What if everything, every planet, every star, every memory, even time itself, is doomed to vanish, not in an explosion, but in a whisper? In this journey across the farthest reaches of physics and imagination, we dive into the ultimate question: how will the universe die? From freezing emptiness to quantum echoes, alien escape plans to cosmic rebirth, this isn't just about the end of stars. It's about the end of everything, and what might still whisper after the silence. The inevitable end. What we mean by the death of the universe. When cosmologists talk about the death of the universe, they're not referring to a cinematic explosion or sudden annihilation. Instead, they're describing a gradual, often cold and drawn-out process where the very fabric of space-time becomes inhospitable to energy, structure, and ultimately life. The universe's death is not one singular event, but the cumulative effect of physical laws playing out over unimaginable timescales. One of the core ideas underpinning this inevitability is the second law of thermodynamics, which states that entropy, the measure of disorder in a system, always increases over time. In simple terms, usable energy becomes less available as systems break down and spread out. In a closed system like the universe, this law suggests that all energy will eventually be so dispersed that no work can be done. Stars will burn out, matter will decay, and even black holes, the universe's last gravitational anchors, will eventually evaporate through Hawking radiation. This state of maximum entropy is what scientists refer to as the heat death of the universe. A key driver toward this end is cosmic expansion. Since the Big Bang, the universe has been expanding, but in the late 1990s, observations of distant supernovae revealed something more shocking: that this expansion is accelerating. This acceleration is attributed to dark energy, a mysterious force that currently makes up about 68% of the universe. Unlike gravity, which pulls things together, dark energy pushes the universe apart. Over time, as galaxies drift further away from each other, interactions between cosmic structures will diminish until, eventually, galaxies are so distant from one another that their light can no longer reach across the growing voids. We'll be left in an isolated cosmic silence, with each galaxy slowly going dark as its stars burn out. There are several dominant theories about how the universe might end, but all are rooted in this idea of irreversible transformation and decay. One of the most discussed is the Big Freeze, which stems directly from the universe's continual expansion. In this scenario, galaxies accelerate away from each other indefinitely. Over trillions of years, stars burn through their fuel and no new stars are born. The universe becomes a cold, dark place as stellar remnants, white dwarfs, neutron stars, and black holes dominate the cosmic landscape. Eventually, even those remnants decay or evaporate, leaving behind only a thin mist of subatomic particles and radiation. Another scenario, though more speculative, is the Big Rip. In this model, dark energy doesn't just accelerate expansion, it increases in strength over time. If it grows strong enough, it could overcome all other forces, including gravity, electromagnetic interactions, and even the strong and weak nuclear forces. Galaxies would tear apart, solar systems would unravel, even atoms would be shredded. The universe wouldn't just become uninhabitable, it would be ripped apart at every level of structure, ending in a final singularity of total fragmentation. While this scenario depends heavily on the nature of dark energy, which we still don't fully understand, it cannot yet be ruled out. Some scientists have entertained the opposite trajectory, that of a big crunch. This model suggests that if the universe's expansion were to slow and eventually reverse, perhaps due to a variable dark energy or gravitational effects on large scales, then the cosmos would contract. Galaxies would rush back toward each other, culminating in a fiery implosion as all matter and energy reconverge into a singularity, a mirror of the Big Bang. While currently considered unlikely due to the confirmed acceleration of expansion, the Big Crunch remains a valuable theoretical possibility for understanding the balance of forces at play. Then there's a more recent and chilling possibility, the vacuum decay scenario. Quantum field theory suggests that our universe may exist in a false vacuum, a metastable state that is not the lowest possible energy configuration. If a transition to a more stable vacuum were to occur, perhaps triggered by a high-energy event or simply a quantum fluctuation, it could generate a bubble of true vacuum expanding at the speed of light. Everything in its path would be annihilated, rewriting the laws of physics as it goes. This isn't a slow death, it's a sudden and complete obliteration of everything, but one we wouldn't even see coming. No matter the scenario, a striking commonality emerges. All predictions assume the eventual demise of complexity. Stars, planets, atoms, and even fundamental particles face entropy's relentless march. On timescales so vast they make our species' entire existence seem like a flicker, the universe becomes simpler, flatter, colder, and less structured. Over quadrillions of years, black holes become the last active players, slowly losing mass via Hawking radiation. In 10-100 years or more, even the largest black holes will vanish, leaving a quiet, empty universe behind, filled with thin, cold radiation and little else. The idea of a universe dying may sound grim, but to physicists, it's simply the long-term consequence of the laws we observe at work today. Energy conservation, thermodynamics, and the observed expansion of space all point to an end that, while distant, is ultimately inescapable. It's not a matter of if, but how. These models also challenge our sense of permanence. Planets, galaxies, even the cosmic background radiation, all are temporary states in a cosmos that constantly evolves. When scientists talk about the death of the universe, they aren't making a prediction for the next century, or even the next billion years. They're sketching the ultimate fate of everything, using the only tools we have: observation, mathematics, and imagination. Understanding the potential death of the universe doesn't just tell us about the end. It illuminates the very structure of reality, revealing that the beauty of the cosmos lies not just in its creation, but in its eventual fading into silence. Dark flow, a hidden force that could rip the universe apart. In 2008, a group of astrophysicists using data from NASA's Wilkinson Microwave Anisotropy Probe, RWMAP, stumbled upon something that didn't make sense: an unexpected and enormous motion of galaxy clusters, all heading in the same direction at extraordinary speeds. These clusters weren't just drifting due to local gravitational effects. They were racing across the universe at up to 2 million miles per hour, moving with eerie precision toward a point in the sky near the constellations Centaurus and Vela. This motion became known as dark flow. What made this finding so unsettling wasn't just the speed. It was that this motion couldn't be explained by any structure within the observable universe. Every known mass, every galaxy, and supercluster had already been factored in. The cosmic web, vast as it is, lacked the gravitational muscle to explain this strange alignment. So where was the force coming from? The universe, as described by the cosmological principle, is supposed to be isotropic and homogeneous at large scales, meaning that, broadly speaking, no matter where you are or where you look, the universe should look and behave the same. Dark flow challenges this principle at its core. If entire galactic clusters are being tugged towards something beyond the known universe, it implies that something massive exists outside the cosmic horizon, beyond the boundary we can observe due to the speed of light and the finite age of the universe. One of the most unnerving explanations is that there may be structures beyond our universe's edge, perhaps massive collections of matter, or even entirely separate universes, that exert gravitational influence on ours. These hypothetical objects might lie in regions of space we can never see, yet they would be capable of pulling galaxy clusters toward them, like cosmic magnets. This raises the possibility that our universe is just a bubble in a much larger multiversal foam, a single membrane or brain among many in higher dimensional space. According to theories like string theory and M theory, the universe could be a 3D surface floating within a multidimensional space with other brains nearby? If so, then gravity, unlike light or electromagnetic radiation, might be able to leak between brains, meaning that some external gravitational source could be affecting our own universe, dragging galaxies along with it in a great invisible tide. The term dark flow was coined precisely because this phenomenon has no visible cause. It mirrors the idea of dark energy and dark matter, forces and substances we infer from their effects but cannot directly observe. However, dark flow is even more mysterious, because unlike dark matter, which we believe permeates our universe, dark flow might originate outside it entirely. The mechanism for detecting this phenomenon involved studying the cosmic microwave background radiation, CMB, the faint afterglow of the Big Bang. As clusters of galaxies move through space, their motion should leave a subtle imprint on this radiation, via a phenomenon called the kinematic Sunyaev-Zeldovich effect. This effect causes slight temperature shifts in the CMB photons when they interact with hot gas moving within the galaxy clusters. By analyzing these shifts, scientists noticed a pattern, a coherent motion across enormous stretches of space, all pointing in the same direction. While the WMAP data suggested this was real, subsequent missions like ESA's Planck satellite have cast doubt on the magnitude or even the existence of dark flow. Planck, which had higher resolution and better sensitivity, found less evidence for this motion. Some astronomers argue the initial WMAP findings were statistical noise or errors introduced during the filtering process. The debate remains unresolved. Some cosmologists remain convinced dark flow is real, pointing to the consistency of its direction and scale, while others see it as an artifact of incomplete data. But if dark flow is indeed real, its implications are cosmic in scale and deeply disturbing. It could mean that our entire observable universe is being subtly drawn toward a gravitational monster lurking beyond visibility. Over vast timescales, this could alter the large-scale structure of the cosmos, potentially even destabilizing it. In the most speculative scenarios, it could signal the eventual destruction or disruption of space-time itself, as our universe is pulled into a collision with another domain of reality. Alternatively, it could be a sign that the Big Bang wasn't the absolute beginning, but merely the birth of our bubble within a far older and larger framework. Dark flow could be the residual memory of events that predate our universe, such as the gravitational echo of other universes forming and collapsing around us. In either case, the presence of such unexplained motion adds another layer to the growing realization that our understanding of the cosmos is far from complete. Just as dark energy shattered the idea that the universe's expansion was slowing down, dark flow challenges the assumption that nothing exists beyond what we can see. If there are forces shaping the motion of entire galaxy clusters that lie outside our observable realm, then the map of reality may be far larger and more dangerous than we imagined. The universe is not a calm and orderly expanse, but a turbulent sea of competing energies and invisible currents. We're passengers on a ship pulled by tides we don't yet understand, heading toward a destination we cannot see. And so, the mystery of dark flow continues to hover like a shadow at the edge of science, unconfirmed, unexplained, and unresolved. But whether it turns out to be a data glitch or a hint of something unimaginably vast, it forces us to ask unsettling questions. What lies beyond the edge of what we can observe? What else is out there, shaping the fate of the universe without our knowledge? Big freeze, when even time itself stops. When people imagine the end of the universe, they often envision something violent and explosive, a big crunch, a catastrophic collision, or perhaps a multiversal rupture. But the most widely accepted and scientifically supported model suggests a far quieter demise. It's not a bang, it's not a rip, it's a freeze. A big freeze, to be precise, the slow, inevitable fading of all heat, light, and motion in the universe, until even the concept of time becomes meaningless. The story of the big freeze begins with a decline, not in temperature, but in creativity. Star formation has already peaked. Around 10 billion years ago, the universe was a cosmic nursery, churning out stars at an extraordinary rate. Now, that era is over. Most of the gas needed to make new stars has already been used up or locked inside long-lived stellar bodies. Every day, the universe gets slightly less luminous and slightly less dynamic. The first stage of the Big Freeze will be marked by the slow extinction of stars. Over the next few trillion years, even the smallest, longest-living red dwarfs will exhaust their hydrogen fuel and become cold, dark remnants. With no new stars forming and all existing stars fading away, galaxies will go dark one by one. When this happens, the universe will enter a new era, one ruled by degenerate matter. These are the remnants of once luminous stars, white dwarfs, neutron stars, and black holes. They will orbit in silence, cooling imperceptibly over vast timescales. These objects don't shine, they merely exist, suspended in a sea of increasingly cold and empty space. One of the most bizarre predictions of this era is the formation of black dwarfs, white dwarfs that have cooled completely, no longer emitting any light. But here's the twist. Not a single black dwarf exists yet. The universe isn't old enough. White dwarfs take trillions of years to cool, meaning black dwarfs are objects of the future, ghosts from a time that hasn't happened yet. And those ghosts may not stay silent forever. Some scientists propose that quantum tunneling could still happen in these objects. Over timeframes exceeding 10-25 years, rare quantum fluctuations might cause these black dwarfs to collapse or even explode in supernova-like events, the last fireworks of a dying universe. These explosions, though few and far between, would momentarily light up a universe that has otherwise gone dark. Meanwhile, something strange is happening to time. In a universe where nothing changes, time begins to lose its meaning. Our understanding of time is deeply tied to change, the ticking of a clock, the orbit of a planet, the decay of a radioactive atom. But in the deep future, when stars no longer shine, when matter barely moves, and when no events of significance occur, what does it even mean to say that time is passing? Without any observable change, time becomes indistinguishable from stillness. In this frozen cosmos, temperature continues to fall. The background radiation that once flooded the universe after the Big Bang continues to dissipate, stretched by the expansion of space until its wavelength becomes effectively infinite. The universe asymptotically approaches absolute zero, the theoretical temperature at which all molecular motion stops. While it may never quite reach this limit, it will get close enough that no meaningful motion or structure can survive. Eventually, even protons may decay. This is a hypothetical process. We've never observed it directly, but many grand unified theories in physics predict it. If true, it would mean that all matter, not just stars, but every atom in the universe, will eventually fall apart, reducing even the most stable elements into radiation and subatomic particles over 1034 years or more. At this point, the universe will be composed of little more than low-energy photons, ghostly neutrinos, and dark energy. No complex systems, no atoms, no stars. Just an unstructured sea of decay products drifting through an endless void. In the midst of all this, black holes will still remain. They are the most stubborn objects in existence, capable of swallowing matter and light, sealed off from the rest of the cosmos by event horizons. But even these titans have a shelf life. According to Stephen Hawking's theory of black hole evaporation, black holes slowly emit radiation over time. For small black holes, this happens quickly. But for stellar mass or supermassive black holes, the process will take 1064 to 10100 years. In that far future, even black holes, the last anchors of gravity, will fade away, leaving behind nothing but a faint hiss of heat. With everything else gone, dark energy continues its work. It doesn't just stretch space, it isolates everything. As the universe expands, distant galaxies will recede beyond our cosmic event horizon, a boundary beyond which light can never reach us. Eventually, every galaxy outside our own becomes invisible, lost forever to the accelerated expansion of space. The Milky Way, by then long merged with Andromeda, becomes an island universe, trapped alone in the dark. And then even that is gone. No stars, no black holes, no galaxies, no change, just entropy. Entropy doesn't just erase order, it erases information. Some physicists argue that as the universe trends toward maximum entropy, even the information encoded in particles and systems will degrade. In this ultimate state of randomness and disorder, not only is there no structure, there may be no memory that structure ever existed. The Big Freeze is not a singular event. It is a process, an erasure of complexity, stretched over incomprehensible timescales. The result is not chaos, but emptiness so complete that even the passage of time loses its relevance. The Big Crunch, a universe collapsing in on itself. What if the universe doesn't end in silence, but in a scream, a final gravitational crescendo that pulls every galaxy, every star, and every atom back into the singularity from which it came? This is the radical vision of the Big Crunch, a theoretical endgame in which the universe stops expanding and begins contracting. It's not just the mirror image of the Big Bang, it's a collapsing echo where space shrinks, temperatures rise, and matter itself may cease to be. For the Big Crunch to happen, one crucial condition must be met. Dark energy must reverse course. Currently, dark energy makes up around 68% of the universe and is responsible for the acceleration of cosmic expansion. But what if it isn't a constant force? Some theories suggest dark energy might decay over time, or even flip sign, turning into an attractive force rather than a repulsive one. If that happened, gravity could regain the upper hand, halting the universe's runaway growth and triggering a slow but unstoppable collapse. As the universe begins to contract, its most distant galaxies would no longer be redshifted, pulled away by expansion. Instead, they would appear to blue shift, rushing toward us as the fabric of space itself contracts. The cosmos would become denser, hotter, and more energetic. Galaxies would collide more frequently, star systems would become unstable, and intergalactic voids would disappear as the universe shrinks in on itself. During this era of contraction, strange things might begin to happen with time itself. In standard thermodynamics, the arrow of time points in the direction of increasing entropy, or disorder. But in a universe that's compressing rather than expanding, some physicists propose that entropy might actually begin to decrease. This has led to wild speculation. Would cause and effect begin to blur? Would time appear to run backward? While these remain open questions, they suggest the collapse phase wouldn't just reverse space, it might twist our understanding of time. As the universe grows smaller and hotter, all known matter would break down. First, planetary systems would be destroyed by gravitational interactions. Then, stars would be ripped apart. Eventually, even atoms would disintegrate into subatomic particles, as the ambient temperature of space climbs into the trillions of degrees. At this stage, quarks and gluons, the constituents of protons and neutrons, would dissolve into a superheated fluid known as quark-gluon plasma, the same state believed to have existed moments after the Big Bang. But the destruction might not stop there. As gravitational forces tighten, black holes across the cosmos could begin to merge, forming colossal supermassive black holes. These black holes, themselves immune to standard forms of destruction, would eventually coalesce into a single, universe-spanning final black hole, absorbing everything within the contracting universe. From stars to dark matter, all structure would be lost in the collapse. This leads to a sobering question. Would the laws of physics survive this final crunch? General relativity breaks down at singularities, the infinitely dense points at the heart of black holes, and potentially at the end of a collapsing universe. Near such conditions, space and time as we understand them cease to function. The constants of nature, things like the speed of light or the gravitational constant, may shift, dissolve, or become meaningless. The very scaffolding of reality might collapse alongside the matter it once organized. Yet not all theories suggest a permanent end. Some models, especially those emerging from quantum gravity, propose that the universe might not shrink into a true singularity. Instead, the collapse could halt at an ultra-small scale due to quantum effects, particularly those involving quantum repulsion at extremely high densities. In such scenarios, rather than ending in oblivion, the universe might bounce, triggering a new expansion phase, essentially a new Big Bang. This is the idea behind cyclic cosmologies, models in which the universe undergoes infinite cycles of expansion and collapse. Each cycle resets the universe, potentially with different physical conditions, constants, or even laws of nature. What we call the beginning may only be one point on a cosmic loop. In this view, the universe doesn't die. It rebirths. But can anything, any information structure or echo, survive from one cycle to the next? In classical physics, information falling into a singularity is lost forever. But some speculative theories, drawing from holographic principles or ideas in string theory, propose that traces of past universes might carry over through quantum fluctuations or dimensional imprints. If that's true, then it's possible that our current universe contains residual fingerprints from an earlier cycle, perhaps even subtle clues encoded into cosmic background radiation or quantum fields. Even more wildly, some cosmologists have hypothesized that life, or at least information, could ride the wave of a collapsing universe into the next. Perhaps encoded into entangled particles or preserved in exotic structures, some aspect of intelligence or memory could survive the crunch, waiting to reawaken in the next iteration of the cosmos. Of course, much of this remains speculative. Observationally, our universe appears to be accelerating, not contracting. If dark energy remains constant or strengthens, the Big Crunch becomes increasingly unlikely, yet it cannot be fully dismissed. If our understanding of dark energy evolves, or if new forces are discovered that interact with it, the collapse scenario might still unfold in some distant future. The Big Rip, when space tears itself apart. Most end-of-the-universe theories involve some sort of settling, a slow freeze, a gravitational collapse, or a heat death stretching across trillions of years. But what if the universe doesn't slow down at all? What if, instead, it speeds up uncontrollably until it tears itself apart, not metaphorically, but literally? This is the scenario known as the Big Rip, a violent, all-consuming expansion driven by a monstrous version of dark energy. At the heart of this theory lies a hypothetical form of dark energy known as phantom energy. Normal dark energy, the kind driving our universe's current acceleration, has an equation of state parameter W close to 1. But phantom energy dips below that with W 1. This means that instead of becoming diluted over time as the universe expands, phantom energy grows stronger. The more space it creates, the more powerful it becomes, in a runaway loop of destruction. This strange behavior causes the universe's rate of expansion to accelerate exponentially, eventually surpassing all other known forces. At first, this would resemble what we see today, galaxies drifting apart faster and faster. But as time goes on, this expansion would begin tearing the universe at every level of structure, from the cosmic web to subatomic particles. Long before the final destruction, the first victims would be galaxy clusters. These massive structures are held together by gravity over billions of light years, but even their immense pull wouldn't be enough. Phantom energy would begin to stretch the space between galaxies until they were flung apart, no longer gravitationally bound. Next would be the galaxies themselves. Approximately 60 million years before the final rip, the Milky Way and its stars would begin to lose their cohesion. Gravity would no longer be strong enough to keep our galaxy intact. It wouldn't explode. It would unravel, stretched like dough on a cosmic table. Stellar neighborhoods would vanish into the expanding dark. As phantom energy's dominance grows, the scale of destruction moves inward. Our solar system, long stable and serene, would come undone. Planets would drift from their stars, orbiting loosely until even those connections vanish. Earth, if still intact, would become a rogue planet, flung alone into the accelerating void, a tomb adrift in a dying cosmos. Then the stars themselves begin to fall apart. Moments before the end, the very processes that power suns, fusion, gravity, and thermal pressure, would collapse. As space itself expands faster than light, the internal forces holding stars together would be overwhelmed, and they'd be torn to shreds, their cores exposed, then unraveled atom by atom. But the Big Rip does not stop at stars or planets. It dives straight into the atomic scale. Normally, atoms are held together by powerful electromagnetic forces. Electrons orbit nuclei due to these forces. But when the fabric of space stretches faster than light can transmit force, even those bonds break. Molecules are ripped apart, then atoms themselves. Protons pulled from neutrons, electrons flung from orbit, and nuclei unzipped. In the final seconds, all known structure would be destroyed. Nothing would be spared, not even the particles that make up atoms. Quarks, the most fundamental building blocks of matter, would be separated from each other, something that doesn't even happen naturally in the most violent conditions of the early universe. The strong nuclear force itself would give way to the stretching of space-time. One of the most chilling aspects of the Big Rip is how it would compress cosmic time. Events that once took billions of years, galaxy collisions, stellar evolution, radioactive decay, would begin happening in weeks, then days, then seconds. In the final moments, cosmic events would blur into one another. For any observer still conscious, the universe's collapse would appear instantaneous, like the frame of a movie burning up in the projector. And then, nothing. Unlike the Big Crunch, which leads to a singularity of extreme density, or the Big Freeze, which fades into an empty void, the Big Rip dissolves everything, including the very fabric of space-time. There is no collapse, no rebirth, no final bang. It's not just that matter is gone. The coordinates of space are meaningless. The metric tensor, which defines how distances and time are measured, ceases to function. The geometry of reality itself breaks down. This apocalyptic outcome is deeply dependent on the true nature of dark energy, something we still don't fully understand. If the universe's current expansion continues at its observed rate, the Big Rip may not occur. But if dark energy turns out to be phantom energy, and W remains below 1, the rip becomes not just possible, but inevitable. Some models estimate that if phantom energy exists and remains consistent, the Big Rip would occur in about 22 billion years. Roughly 200 million years before the rip, galaxy clusters fall apart. 60 million years out, galaxies disintegrate. 3 months before the end, solar systems collapse. In the final minutes, stars die. And in the last 10-19 seconds, atoms and particles vanish. The Big Rip doesn't leave behind a void. It doesn't leave anything. There is no after, only the absolute erasure of all dimensions and matter. From every atom to the largest supercluster, everything that ever existed becomes unstitched by the universe's own expansion. Vacuum decay. The universe could end without warning. Imagine a cosmic doomsday so silent, so unstoppable, and so absolute that we wouldn't even realize it had begun. No countdown, no warning. One moment, everything exists. Galaxies, stars, atoms, life. The next, gone. Not destroyed, but rewritten by a universe that suddenly decided to become something else entirely. This is the nightmare scenario of vacuum decay, a theoretical endgame rooted in the deep mathematics of quantum field theory and the precarious nature of the vacuum we live in. In physics, the term vacuum doesn't mean empty space. It refers to the lowest possible energy state of a field. But not all vacuums are created equal. Some are true vacuums, the absolute lowest possible state, while others are false vacuums, local minima that feel stable but are actually perched precariously on the edge of collapse. And according to our best understanding of the Higgs field, the field responsible for giving particles mass, we might be living in a false vacuum right now. The discovery of the Higgs boson in 2012 confirmed the existence of the Higgs field. But the particle's mass, around 125 GeV, combined with the mass of the top quark, created an unsettling realization. These values place the Higgs potential in a range that implies metastability. In other words, the current configuration of our universe might not be the true ground state. Instead, we could be living in a temporary bubble, suspended in a higher energy vacuum that could one day pop. If a lower energy state exists, quantum tunneling, the spontaneous shift from one state to another, could cause a small region of space to transition to the true vacuum. This would create a bubble of true vacuum, a region with new physics, new laws, and a new energy minimum. The catch: that bubble would be incompatible with everything we know. Inside it, atoms may not form, forces may behave differently. Matter itself may not be stable. This bubble would begin microscopically, perhaps at the subatomic scale, but it wouldn't stay small. Driven by the energy difference between the false and true vacuums, the bubble would expand at the speed of light, devouring all space in its path. You wouldn't see it coming. There'd be no radiation, no shockwave, no blaze, just instant annihilation. Wherever the bubble reaches, reality as we know it would be instantly rewritten or erased. What's especially horrifying is that there is no defense against this. Since it travels at the speed of light, no information about its arrival can precede it. If such a bubble began forming in some distant corner of the cosmos, it could already be on its way to Earth. By the time the photons of distant stars twinkle in the night sky, the decay bubble could already be swallowing galaxies along the way. And we wouldn't know until we didn't exist anymore. Inside this new vacuum, the laws of physics would be entirely different. The constants we take for granted, the speed of light, Planck's constant, the strength of gravity, could all change. Molecules, chemistry, and biology may be impossible. The very nature of space, time, and causality might be rewritten. While the true vacuum could be more stable, it would be utterly alien. In this sense, vacuum decay is more than just destruction. It's cosmic metamorphosis. Our universe wouldn't die in fire or ice, but in a quiet transition to a completely different reality, one that might host new physics, perhaps even a new universe, but without any of the structure or continuity from the old one. There are also fringe scenarios where such a vacuum decay could be triggered artificially, say by a high-energy particle collision. When the Large Hadron Collider, LHC, first began smashing protons together, some members of the public feared it might spark such a catastrophic event. Physicists quickly dismissed this as extremely unlikely, and so far correctly, but the theoretical foundation isn't completely absurd. If the right conditions were met, vacuum instability could be seeded by enough concentrated energy. Thankfully, the energy scales required are vastly higher than what any human-made collider could achieve, but nature could still do it. Perhaps the most chilling idea of all is that vacuum decay may already be happening. Somewhere, out in the vast unknown of the cosmos, a region could have already transitioned. A decay bubble could have formed, silently expanding through space for millions of years. If it started far enough away, its edge hasn't reached us, yet. But it's coming, and when it does, it won't announce itself. From a philosophical standpoint, vacuum decay is a reminder of the fragility of existence. We often think of the universe as a stable platform, something constant, predictable, foundational. But in reality, the fields that underpin our reality are mathematical structures balanced in energetic landscapes we're only beginning to understand. What we call permanent might simply be a pause in a larger story. It also raises deep questions. What determines whether a vacuum is true or false? If our universe began in a Big Bang, why didn't it fall into the true vacuum immediately? Are there universes where such decay has already occurred, or is occurring in real time? And what happens after the decay bubble has consumed everything? One speculative answer is that the new vacuum could become the seed of a brand new universe. It might expand infinitely, just like ours did after the Big Bang, but under new rules. From the ashes of one cosmos, another could rise, not as a continuation, but as a replacement. Perhaps this is how universes evolve, not through growth or collapse, but through quantum leaps into new forms. Yet none of that would matter to us. In our frame of reference, vacuum decay means total and instantaneous erasure. There's no time to say goodbye, no warning light on the dashboard of existence, just the end. So as we gaze into the night sky, comforted by the stability of stars and the rhythm of galaxies, remember, the most terrifying fate of the universe might already be on the way, and we'd never even feel it. The last black holes, a universe dominated by darkness. When all matter collapses into black holes and then they evaporate. Imagine a universe so old that stars no longer shine, galaxies no longer swirl, and even atoms have decayed. The only remaining structures are black holes, silent, invisible, and scattered sparsely across the void. Welcome to the black hole era, a future epoch in which these dark titans outlast every other trace of cosmic activity. They are the universe's final monuments, and they too will eventually disappear. After the last stars exhaust their fuel and stellar remnants cool into invisible black dwarfs, black holes become the universe's final complex structures. This transition doesn't happen suddenly. Over trillions of years, gravity gradually pulls matter into denser and denser configurations. The most massive stars collapse into black holes. Mergers between neutron stars and other compact objects feed this growing population. Eventually, most of the universe's mass will be locked inside black holes, but they won't remain crowded. Over time, gravitational interactions, especially slingshot effects between orbiting objects, will eject all remaining matter from galactic cores. Rogue white dwarfs, brown dwarfs, and planetary bodies will be flung into the darkness, while others are consumed. This chaotic pinball game ends when only the black holes are left, drifting through a universe devoid of stars, light, or order. Yet even in this silent epoch, some black holes may form new, eerie ghost solar systems. As rogue planets and brown dwarfs wander through interstellar space, they may be captured into orbit around isolated black holes. Without stellar light, these systems would be entirely dark, their motion governed only by gravity. The only visible trace, if one could see it, would be the gravitational lensing of background light, warping around the black hole's invisible core. While stellar mass black holes are impressive, the real giants, supermassive black holes, dwarf them in both scale and longevity. Lurking at the centers of galaxies, these monsters range from millions to billions of times the mass of the Sun. Long after every galaxy has evaporated, these supermassive remnants will persist, taking up to 10 or 100 years to finally disappear. Their slow demise will be one of the last processes to occur in the universe. How do black holes die? Through a process predicted by Stephen Hawking in the 1970s, black hole evaporation. Due to quantum effects near the event horizon, black holes can emit tiny amounts of radiation, causing them to gradually lose mass. At first, this process is glacial, barely noticeable even over trillions of years. But as the black hole shrinks, the emission increases exponentially. In its final moments, a black hole could release an enormous burst of energy, evaporating completely in a flash. Some theorists speculate that long after all normal black holes have faded, quantum fluctuations in the near absolute zero void could still spontaneously generate new micro-black holes. These would exist briefly before evaporating, injecting occasional blips of mass and energy into an otherwise inert cosmos. Even in the universe's endgame, quantum uncertainty might continue to stir. But perhaps the most haunting question of all is, what happens to the information inside a black hole? According to classical physics, anything that falls into a black hole is lost forever, its structure erased beyond the event horizon. Yet this contradicts quantum mechanics, which demands that information cannot be destroyed. This paradox has puzzled physicists for decades. Some believe that information is somehow encoded on the event horizon itself, preserved in a two-dimensional format, the so-called holographic principle. Others suggest that entangled particles outside the black hole may still remember the internal state. But many fear that black holes represent a fundamental breakdown in our understanding of reality, where information simply ceases to exist. The final answer may lie in a future theory of quantum gravity, or it may never be fully resolved. One thing is clear: the black hole era will last longer than every other epoch combined. From the birth of the first stars after the Big Bang to the end of star formation a few trillion years later, all of that cosmic history will be a fleeting prologue compared to the near-eternal reign of black holes. From the 1010 years, when star formation ends, to 10 of 100 years, when the last supermassive black hole evaporates, this era will dominate cosmic time. Even during this era, black hole mergers may still occur. Though increasingly rare, gravitational interactions between isolated black holes could lead to slow-motion collisions. These events might generate gravitational waves, ripples in spacetime, echoing faintly across the darkness. But as space expands and matter spreads thin, these interactions will become vanishingly scarce. And then, silence. The final act in this cosmic opera arrives when the last black hole evaporates. There is no remnant, no skeleton, no lingering core. The black hole simply ceases to exist, leaving behind a puff of low-energy radiation. The temperature of this radiation would be near absolute zero, contributing to the thin haze of entropy already spread across the cosmos. No light, no gravity, no matter. What remains is a flat, empty, structureless universe. Space still exists, but without curvature, without features, and without boundaries. Time may continue, but with no events to mark its passage, it becomes a meaningless dimension. This is the final quiet, the ultimate entropy. A universe that was once ablaze with stars, bursting with energy, expanding with potential, ends not in chaos, but in complete uniformity. The last black holes, once the mightiest structures in existence, leave behind nothing. No shadow, no gravestone, only the faintest whisper of radiation in a sea of cold. Hawking radiation, the slow death of black holes. Black holes were once thought to be eternal, cosmic traps from which nothing could escape, not matter, not light, not even time. But in 1974, Stephen Hawking turned this assumption on its head. By combining quantum mechanics with general relativity, he proposed that black holes are not completely black after all. They glow, not brightly, not quickly, but they do emit energy, and in doing so, they slowly, inevitably die. This radiation, now known as Hawking radiation, arises from a strange but well-established phenomenon in quantum physics, the temporary existence of virtual particles. In a vacuum, space is never truly empty. Instead, it constantly churns with pairs of particles and antiparticles that blink into and out of existence in unimaginably short timescales. Normally, these pairs annihilate each other instantly, but near the edge of a black hole, something remarkable can happen. If a virtual particle pair appears near the event horizon, the point beyond which nothing can escape, tidal forces and extreme curvature of spacetime can separate the pair. One particle may fall into the black hole while the other escapes into space. This lone survivor becomes a real particle detectable to the universe, a quantum leak from a region previously considered sealed forever. But conservation of energy demands that the escaping particle's energy must come from somewhere. That somewhere is the black hole itself. By emitting this radiation, the black hole loses mass. Over time, as more and more of these particles escape, the black hole gradually shrinks. It evaporates, not in a flash, but in a cosmic whisper lasting trillions upon trillions of years. The rate of this evaporation is minuscule at first. For black holes the size of a star, the radiation is so faint it's nearly impossible to detect. A solar mass black hole would take around 1067 years to completely evaporate. That's more than 1 billion trillion times the current age of the universe. But the truly fascinating twist is that this process accelerates as the black hole loses mass. It gets hotter, it radiates faster, and in its final stages, it may release an enormous burst of energy, a last bright gasp before disappearing completely. This means that smaller black holes die faster than large ones, and this opens up an intriguing possibility. Shortly after the Big Bang in the chaotic early universe, tiny primordial black holes may have formed, some with masses less than a mountain. These hypothetical black holes would be nearing the ends of their lives right now, potentially releasing bursts of gamma rays or high-energy particles. Some researchers even believe we could detect these signals with the right instruments, providing the first observational evidence of Hawking radiation. But Hawking radiation isn't just about evaporation. It opened a portal between three of physics' deepest theories: quantum mechanics, general relativity, and thermodynamics. This single prediction forced physicists to see black holes not just as gravitational anomalies, but as thermodynamic systems, objects with temperature and entropy. In fact, Hawking's work built upon earlier insights by Jacob Bekenstein, who argued that black holes must have entropy, a measure of disorder or information content. Hawking showed that this entropy is proportional to the surface area of the event horizon, not its volume. That revelation gave rise to the holographic principle, the idea that all the information within a volume of space can be encoded on its boundary, much like a 3D object represented by a 2D hologram. This leads to one of the greatest unsolved mysteries in physics, the black hole information paradox. If a black hole evaporates and disappears, what happens to the information about the particles that fell in? Does it escape, encoded in the Hawking radiation? Is it preserved somehow on the horizon? Or is it lost forever, violating the fundamental laws of quantum mechanics? The implications are massive. If black holes can destroy information, then unitarity, a core principle of quantum theory, is violated. If they don't, then we need a complete theory of quantum gravity to explain how the information is preserved. Either way, Hawking's insight forces us to confront deep inconsistencies in our understanding of the universe. Despite its theoretical power, Hawking radiation has never been directly observed. It's incredibly faint, easily drowned out by other cosmic signals. But the math is compelling, and the theory has survived every challenge thrown at it. In fact, analogues of Hawking radiation have been demonstrated in laboratory settings, such as using superfluid helium or optical event horizons in laser-induced media. These experiments don't involve real black holes, but they mirror the physics, offering tantalizing glimpses into what might one day be verified in space. And what of the end? The final stage of black hole evaporation, especially for small or primordial black holes, could be spectacular. As the object shrinks and its temperature soars, it may release a powerful burst of radiation, possibly detectable by gamma-ray telescopes or cosmic ray detectors. Some speculative theories suggest exotic phenomena may emerge: unknown particles, flashes of high-energy light, or even tunnels to other dimensions. It's entirely possible that the final breath of a dying black hole will reveal more about the structure of the universe than anything we've seen so far. So while black holes may feel like cosmic dead ends, places where time halts and matter vanishes, Hawking radiation shows they are anything but inert. They evolve, they interact with the quantum vacuum, and they eventually disappear. Proton decay, if matter itself isn't stable. When we look around us, at the walls, our hands, the stars in the sky, we assume the matter that makes up our world is stable, permanent, eternal. But what if it isn't? What if the proton, the most basic component of all atomic nuclei, is actually ticking like a slow cosmic time bomb, destined to decay, taking the universe with it, one particle at a time? This haunting possibility lies at the heart of one of physics' most profound and least understood questions. Is matter truly stable? Protons are everywhere. They are one of the key building blocks of atoms, which in turn form molecules, planets, and people. For decades, they were believed to be absolutely stable. After all, no one had ever seen one decay. But modern theoretical physics, particularly through the lens of grand unified theories, GUTS, suggests otherwise. GUTS attempt to unify the three fundamental forces, electromagnetism, the weak nuclear force, and the strong nuclear force, into a single framework. In many of these models, particularly SU-5 and SO-10, proton decay is a natural consequence. These theories predict that protons should eventually transform into lighter particles, such as positrons, anti-electrons, and neutral pions, which themselves decay rapidly into gamma rays. But here's the catch. If proton decay happens, it's incredibly slow. Experimental efforts, like those at Japan's Super Kamiokande detector, have searched for it by watching trillions of tons of water over many years. So far, not a single confirmed event has been seen. The implication? If decay occurs, the average proton must live at least 1034 years, a lifespan nearly a billion times the current age of the universe. That might seem reassuring. But cosmologists don't think in centuries or millennia, they think in eons. And over the truly vast timescales projected for the universe's future, proton decay becomes more than relevant. It becomes inevitable. Imagine the universe in its deep twilight. Stars have long since died. Black holes are slowly evaporating. Planets have been cast into the void. In this silence, the remaining atoms, cold, stable, solitary, might begin to crumble. One by one, their protons decay, emitting flashes of radiation as they vanish. Entire molecular structures disintegrate into elementary particles, and with every decaying proton, the universe loses a bit more of its matter. The implications are staggering. It means that no physical object, no rock, no diamond, no neutron star, is truly permanent. Even if shielded from all external forces, even if frozen to near absolute zero, the atoms themselves will fall apart. Permanence, it seems, is an illusion painted over an ocean of slow instability. And the result? A cosmos no longer made of matter, but of radiation and subatomic fragments. The process would be slow, almost unnoticeable at first, but across trillions of years, it would transform the entire universe, from a place filled with particles and complexity to one composed entirely of photons, leptons, and energy. The decay of protons would also signal a thermodynamic shift. Until now, the universe has been a balance between matter and energy, order and entropy. But once protons begin to vanish, entropy wins outright. With no more stable matter, there are no more structures to organize, no more systems to evolve. Just a spreading, thin mist of radiation in a geometry devoid of form. If this happens after the last black hole has evaporated, as predicted, then proton decay becomes the final death knell, the last act of physics, the ultimate transition from a dynamic universe to a cold, empty, and irreversible entropy field. Yet this isn't just an existential concern. It's a litmus test for our understanding of physics. The Standard Model, our current best theory of particle interactions, does not predict proton decay, but virtually all GUTS do. Therefore, the discovery or continued absence of proton decay could either confirm or destroy decades of theoretical work. That's why experiments like Super Kamiokande and its successor, Hyper Kamiokande, are so important. These enormous underground detectors are filled with ultra-pure water and surrounded by sensitive light sensors. When a proton decays, it should produce a cascade of detectable signals, tiny flashes of Cherenkov radiation that indicate the end of a once stable particle. Despite no detection so far, the experiments continue. Every non-result pushes the expected proton lifetime higher, but also brings us closer to knowing whether matter itself has a shelf life. Some theoretical models suggest more exotic variations of proton decay, such as decay rates that vary with environment, energy levels, or even cosmic expansion. Others propose that proton decay might be connected to deeper questions of quantum gravity, or even the early inflationary period of the universe, when symmetry breaking may have planted the seeds for instability. In the vast scope of cosmic time, the stakes couldn't be higher. If protons are truly eternal, matter can persist forever, even in isolation. But if they decay, the universe is destined to fade into radiation, with all traces of structure and identity eventually erased from existence. This leads to one final poetic implication. The universe might not end in a bang or a freeze or a rip, but in a crumble. A quiet unbuilding of everything, starting not with galaxies or stars, but with the very protons in your body, the air, the earth, all of it returning to the quantum fog from which it came. Dark energy domination. Why the universe is rushing toward isolation. In 1998, two independent teams of astronomers made a discovery that upended everything we thought we knew about the universe. Its expansion isn't slowing down, it's speeding up. This acceleration was unexpected, unaccounted for, and utterly transformative. To explain it, scientists introduced a new force of nature, dark energy, a mysterious pressure embedded in the fabric of space itself. Now, over 2 decades later, we realize that this force is doing more than just stretching space. It's reshaping the fate of the cosmos. Today, dark energy accounts for an estimated 68% of the total energy content of the universe. Matter, both visible and dark, makes up less than 32%, and that ratio is shifting further in dark energy's favor with every passing epoch. Unlike matter, which dilutes as the universe expands, dark energy appears to remain constant in density, meaning that the more space there is, the more dark energy exists. This leads to a runaway expansion. More space creates more dark energy, which in turn drives even faster expansion. In the early universe, gravity had the upper hand. Galaxies formed, stars clustered, and cosmic webs grew dense and structured. But that age is ending. In our current epoch, the cosmic transition era, dark energy has begun to take over. In a few tens of billions of years, it will completely dominate the large-scale behavior of the cosmos. As this domination grows, the most immediate consequence is isolation. Galaxies that are not gravitationally bound to our own will recede beyond our cosmic horizon. This doesn't mean they're moving through space faster than light. It means space itself is expanding between us faster than light can travel. As a result, their light will never reach us, no matter how long we wait. This leads to the emergence of a cosmological event horizon, much like a black hole's event horizon. It defines the boundary of what can ever be seen or influenced. Anything beyond it is permanently disconnected from us. Eventually, only the local group, the Milky Way, Andromeda, and a few dozen smaller galaxies, will remain visible. Everything else will be swallowed by the void. Ironically, even as the universe expands, the observable universe shrinks in content. Distant galaxies that once informed us of cosmic history will vanish from view. Future civilizations may find themselves marooned in isolated pockets of space, unable to observe the rest of the cosmos, potentially believing they are the only structures that ever existed. But it's not just about what we can see. As dark energy tightens its grip, it brings cosmic structure formation to a halt. Galaxies that haven't yet formed won't. Matter becomes too diffuse to clump together under gravity. Star formation slows, then stops. Cosmic activity dwindles. The large-scale universe begins to coast towards stillness. This creates an eerie paradox. From the inside, the universe may always look cosmically young. Dark energy dilutes or erases long-distance relics like the cosmic microwave background, CMB. In the far future, the CMB will be redshifted so dramatically that it becomes undetectable, removing the most important clue that the Big Bang ever happened. Advanced civilizations living billions of years from now might see only their own galaxy surrounded by darkness. No expansion, no background radiation, no cosmic history. From their perspective, the universe might appear unchanging, eternal, and small. Dark energy could even affect the passage of time itself. While our clocks keep ticking, the large-scale flow of cosmic time becomes increasingly disconnected from cause and effect. As expansion accelerates, the rate of change in the universe plummets. With fewer structures forming and less energy interacting, time becomes harder to define in any meaningful way. And yet, for all its dominance, we don't really understand what dark energy is. It could be a cosmological constant, an intrinsic property of space as Einstein originally suggested. But it might also be a dynamic field, something that evolves with time, like quintessence. If that's true, then the future isn't fixed. Dark energy might weaken, change polarity, or even disappear, reopening the door to cosmic collapse or other exotic fates. There's also the possibility that dark energy is not a fundamental force at all, but a misunderstanding of gravity on cosmic scales, a clue that our current theories are incomplete. Some modified gravity models like FR gravity or scalar tensor theories try to explain the acceleration without invoking a new energy form. But these models remain speculative, and none match observations as cleanly as the cosmological constant. Yet, what's especially haunting is that we live in a special moment, one of the few periods in the universe's history when dark energy and matter are comparable in scale. This balance is fleeting. In the past, matter ruled. In the future, dark energy will overwhelmingly dominate. That means humanity exists during a cosmic midlife crisis, a transition period of complexity, structure, and observability that may never happen again. Phantom energy, dark energy's deadlier cousin. As if dark energy weren't unsettling enough, silently accelerating the universe's expansion, isolating galaxies and pushing us toward a frozen end, theoretical physics allows for something even worse: phantom energy. It's dark energy's rebellious cousin. A hypothetical force that doesn't just stretch the cosmos but tears it apart, piece by piece, in a nightmare scenario known as the Big Rip. To understand phantom energy, you need to grasp one key number, the equation of state parameter, usually denoted by W. For dark energy, W represents the ratio of pressure to energy density. When W equals sign 1, you get the classic cosmological constant, Einstein's original formulation of a vacuum energy that stays constant over time. This is the leading model we use today to describe dark energy. But phantom energy is what happens when W drops below 1. At first glance, that might seem like a technical tweak, a small numerical change, but in physics it's a profound violation of nature's rules. Why? Because W1 breaks the dominant energy condition, a cornerstone of general relativity that prevents things like faster-than-light signals or negative energy densities. Phantom energy throws that out the window. It introduces negative kinetic energy, meaning that instead of diluting with expansion, it amplifies. The more the universe expands, the more phantom energy appears. It's a feedback loop with no off switch. That runaway effect is what makes phantom energy so dangerous. In our current epoch, dark energy, with W1, is slowly accelerating the expansion of the universe. But if W is less than 1, even slightly, that acceleration increases exponentially. The result isn't just isolation. Like in the Big Freeze, it's destruction on every scale. Galaxies disband, stars rip apart, planets shred, and eventually even atoms are torn to bits. This is the Big Rip. The process starts subtly. First, gravitationally bound systems like galaxy clusters begin to separate. Then galaxies themselves are pulled apart, their stars flung into the void. Next, solar systems unravel. Planets no longer orbit stars, instead drifting off as space grows more hostile. Eventually, even the Earth would be ripped from its orbit. But phantom energy doesn't stop at solar systems. It keeps going, accelerating, until even individual planets are torn asunder by the expanding space-time. Then comes the disintegration of molecules, atoms, and finally the subatomic particles themselves. The very fabric of matter is unraveled by a force that simply won't stop expanding. This isn't a collapse. It's a disassembly of reality. In the final phase before the rip, time itself begins to compress. Events that once spanned billions of years, like galaxy formation or stellar lifespans, begin to occur in shorter and shorter windows. As expansion speeds up, the intervals between cosmic events shrink, creating a bizarre distortion of temporal experience. Near the end, vast cosmic changes might unfold in mere seconds. And then, the end, the Big Rip singularity, a moment when the scale factor of the universe, the measure of spatial separation between points, becomes infinite in finite time. Space is so stretched that distances lose meaning, light cannot travel, and even the equations that define space-time itself break down. Unlike the Big Bang or Big Crunch, which involve compression into a point, the Big Rip ends in infinite expansion, a boundaryless explosion of distance, with nothing left to hold anything together. And yet, it might not be the final end. Some speculative theories suggest that the runaway energy of phantom expansion could destabilize the vacuum of our universe, triggering a quantum event like vacuum decay that causes the universe to tunnel into a new state. In this view, the Big Rip might not be an end, but a transition into a new phase of existence, governed by different physics altogether. Whether such a rebirth is possible, however, is entirely theoretical. We have no observational evidence for phantom energy. In fact, current measurements, from supernova surveys, baryon acoustic oscillations, and cosmic microwave background observations, suggest W is very close to 1. But even a slight dip below that value would make phantom energy mathematically viable, and the Big Rip a terrifyingly real possibility. That's why scientists continue to refine their estimates of W. The tiniest deviation below, one could hint that the universe isn't headed for a gentle coast into heat death, but for a catastrophic stretch into cosmic oblivion. It's also worth noting that phantom energy would impact more than expansion. Its strange properties could influence fundamental constants, alter the thermodynamics of black holes, and even challenge quantum field stability. It's not just a death sentence. It's an indication that our current understanding of physics might be incomplete. Entropy, the silent march toward disorder. There is no force more quietly relentless than entropy. It doesn't explode like a supernova or rip space apart like phantom energy. It doesn't bend time, crack space-time, or collapse stars. And yet, over enough time, entropy wins against everything. It is the universal bookkeeper of disorder, the law that ensures everything eventually decays, disperses, and fades into silence. At its core, entropy is about probability. The second law of thermodynamics tells us that in a closed system, entropy, or the amount of disorder, will always increase. Why? Because disorder is simply more likely than order. There are more ways for things to be messy than to be organized. A glass can shatter in a million ways, but there's only one way for all those shards to reassemble. As the universe ages, entropy climbs, not because anything wants it to, but because it's statistically inevitable. And here's the strange part. The universe began in an extremely low entropy state. After the Big Bang, matter and radiation were distributed almost perfectly evenly. That's bizarre. An even distribution is highly ordered, like stacking a deck of cards in perfect numerical order. That low entropy gave rise to the universe's structure. Gravity pulled matter into galaxies, stars, planets, and people. But that structure came at a cost, a dramatic increase in overall entropy. You see, every act of creation, whether it's the birth of a star or the rise of a civilization, produces more entropy than it removes. A star converts hydrogen into helium, releasing light and heat that eventually spread across space, increasing disorder. A human body builds proteins and cells but gives off heat in the process, driving entropy up. Order is built locally, but entropy is exported globally. There's no free lunch, not even for the universe. And this is where the cosmic consequences become profound. Over time, more and more energy becomes unusable, locked in random, low-temperature radiation or thinly dispersed particles that can no longer do work. This means the universe is headed toward thermal equilibrium, a state where temperatures are equal everywhere and no energy gradients exist. Without gradients, you can't have engines. You can't have complexity. You can't have life. This is the heat death of the universe. the natural endgame of entropy. Not an explosion, not a collapse, but a slow, inevitable fading into darkness and stillness. The stars go out, the black holes evaporate, even protons decay. Eventually, there's no structure left to destroy, only a uniform, featureless fog of subatomic particles and long-dead radiation. But entropy isn't just a predictor of physical decay. It's the very reason we experience time. The arrow of time, the one-way flow from past to future, is not a built-in feature of physics. The laws of motion, electromagnetism, and even quantum mechanics are all time-symmetric. What makes time feel directional is entropy increasing. It's the reason we remember the past but not the future, the reason we age, the reason you can't unburn a piece of toast or unmix cream from coffee. Without entropy, time would be meaningless. And if that weren't unsettling enough, some physicists believe that entropy may eventually erase even information itself. Not just the arrangement of matter, but the records, the signatures, the memories of whatever existed. All distinctions between past states may blur into nothingness. The idea that information can never be destroyed is challenged by entropy's unrelenting advance. Some argue that even the story of the universe might eventually fade. What makes entropy so humbling is that it rules every level of reality, from quantum interactions to thermonuclear fusion, from steam engines to digital computers. Entropy is always at work, pushing systems toward disorder. It's the reason perpetual motion machines are impossible. Energy always leaks out as waste. You can never get more than what you put in. Nature has a built-in inefficiency, and it's called the second law. Entropy also governs more than just physical systems. It shapes the evolution of stars, the chemistry of life, even the rise and fall of civilizations. Human societies build towering cities, global trade networks, and intricate cultures, all requiring massive energy consumption. That energy use increases entropy, both environmentally and thermodynamically. Every moment of order we create pushes the universe deeper into disorder. Yet entropy isn't evil, it's not malicious. It's simply the natural trend of complex systems with energy, and it's also what allows change. A perfectly ordered system doesn't evolve, it doesn't grow, it just sits there, inert. Entropy gives us evolution, movement, novelty, at the cost of permanence. The entropy of the universe will eventually reach its maximum, a state where everything is so evenly distributed that no differences remain. No hot or cold, no motion or rest, no here or there. Just homogeneity, just a flat, infinite, undisturbed silence. No stars, no memory, no clocks, nothing to change, and nothing to measure change by. The death of stars, when the lights go out. In the beginning, the universe was dark. Then came light. The first stars ignited, scattering brilliance across the black canvas of space. For billions of years, stars formed, lived and died in dazzling cycles that gave birth to galaxies, planets, and life itself. But this luminous era will not last forever. One day the lights will go out, and the universe will return to darkness. Star formation is already past its golden age. Roughly 10 billion years ago, galaxies were veritable factories, churning out stars at breakneck pace. Cold hydrogen gas, the primary ingredient for stellar birth, was abundant. But gas is a finite resource. As time went on, that fuel was slowly consumed or locked away in stars, planetary systems, and black holes. Today, the rate of star formation has dropped by more than 90% from its peak, and it continues to decline. Eventually, galaxies will run out of gas altogether. The interstellar medium, the thin soup of gas and dust between stars, is being used up faster than it's replenished. When it's gone, galaxies will become sterile, unable to form new stars. What remains are the aging stars from earlier generations, slowly exhausting their fuel in a universe that's already gone quiet. Among these survivors, red dwarfs will linger the longest. These small, cool stars are the most common in the universe, and also the most efficient. They burn their hydrogen fuel very slowly, allowing them to live for trillions of years. far longer than the universe has existed so far. In a future devoid of stellar nurseries, red dwarfs will carry the torch of light, burning low and steady, while everything else fades. But even they can't last forever. When red dwarfs finally exhaust their fuel, they don't explode like their massive cousins. Instead, they cool and dim, fading into inert, cold objects known as black dwarfs, hypothetical stars that no longer emit light or heat. None exist yet. The universe is too young. But in trillions of years, it will be filled with them. This marks a pivotal shift. Stellar fusion, the process that powers stars and creates heavier elements, will come to an end. There is no replacement for this engine. Without stars, there are no more elements being forged in stellar cores, no ultraviolet light to drive chemical reactions, no solar winds to energize planetary atmospheres. Cosmic metabolism grinds to a halt. There may still be rare flashes of brilliance. In some binary systems, two white dwarfs, the dense remnants of dead stars, can spiral into one another and collide. These events may trigger type Ia supernovae, brief but powerful explosions that momentarily light up the dark. But such collisions will become increasingly rare. The universe will become a graveyard, lit only by the occasional flicker of cosmic ghosts. Over time, galaxies will transform into silent cemeteries, populated by white dwarfs, neutron stars, black holes, and black dwarfs. Stellar corpses will drift through space, remnants of a universe that once burned with brilliance. There will be no new stars to replace the ones that die, only the echoes of what once was. This has consequences far beyond mere brightness. Stars play a crucial role in maintaining planetary conditions. They warm planets, drive weather, and enable the chemistry necessary for life. Without stars, planets grow cold, their surfaces freezing over, their atmospheres collapsing. Life, if it still exists at that point, would need to find a way to survive in the dark, without starlight, or it too will perish. Even the night sky itself will fade. As cosmic expansion continues and dark energy accelerates the pace, distant stars and galaxies will vanish beyond the cosmic horizon. Future observers, if any exist, will look up and see no constellations, no Milky Way, no Andromeda. Only darkness. The sky will no longer tell stories. It will hold no memory of the past. The cosmic timeline paints a haunting picture. In a few trillion years, the last red dwarfs will fade. For trillions more, the universe will coast in darkness. Fusion will be a memory. All that remains will be inert mass and the slow ticking of entropy, wearing down the last reserves of energy. The night will stretch longer and darker than anything we can imagine, not for centuries or millennia, but for eternities. The last light, white dwarfs and black dwarfs. When a star dies, it doesn't always explode. Most stars, in fact more than 97% of them, choose a quieter path. After billions of years burning hydrogen into helium, they don't go out with a bang, but with a long glowing whisper. These stars end their lives as white dwarfs, the fading embers of stellar fire, destined to become the last visible lights in a universe growing steadily colder and darker. A white dwarf is born when a star like our Sun exhausts its nuclear fuel. No longer able to support itself against gravity through fusion, the star expels its outer layers, forming a glowing planetary nebula, while its core collapses into a dense, compact object roughly the size of Earth. This remnant is the white dwarf, hot, incredibly dense, and no longer powered by fusion. Instead of generating energy, a white dwarf simply radiates away its stored thermal heat. Initially, these remnants can be extremely hot, glowing with a brilliant white or blue-white light. But they have no internal energy source to replenish their heat, so they begin an immensely slow cooling process. It is this cooling, not a catastrophic event, that defines the next phase of their existence. Over billions and then trillions of years, a white dwarf cools gradually, dimming like a dying coal. The process is so slow that the universe isn't old enough for any white dwarf to have yet completed it. The oldest white dwarfs observed today are still glowing faintly, and none have yet cooled enough to become what theorists call a black dwarf, a stellar remnant so cold and dim that it emits no visible light. One of the most fascinating discoveries in recent years is that as white dwarfs cool, they begin to crystallize. This isn't just poetic metaphor, it's literal. The intense pressure inside the white dwarf causes its carbon and oxygen atoms to lock into a crystalline lattice, effectively turning the star into a giant diamond floating through space. The universe's future is filled not with burning suns, but with frozen gems the size of planets, cosmic jewelry in the endless dark. And in that future, white dwarfs will become the last sources of visible light in the cosmos. Long after the last red dwarf flickers out, after galaxies grow quiet and stellar collisions cease, the cooling glow of white dwarfs will be the universe's final candlelight. They mark the twilight of thermonuclear fusion, a sunset billions of years long. Eventually, though, they too will fade. As their temperatures drop below the threshold for visible light, they will transition into black dwarfs. These hypothetical objects are the true endpoints of stellar evolution, invisible, cold, and utterly inert. No black dwarfs exist yet. The universe, at just under 14 billion years old, is far too young for even one white dwarf to have completed its slow descent into darkness. But in quadrillions of years, they will be everywhere. Black dwarfs may no longer shine, but they still exist. They retain mass and gravitational influence, silently tugging on nearby remnants, planets, or rogue objects. They will form vast, unlit structures drifting through the cold, the bones of a cosmos that once blazed with starlight. But there may still be surprises. Some physicists theorize that black dwarfs, after unimaginable spans of time, may not remain entirely inert. Due to quantum tunneling, or perhaps even proton decay, black dwarfs could undergo sudden transformations. In ultra-rare scenarios, they might collapse further, ignite fusion in isolated reactions, or even detonate in weak thermonuclear supernovae. These would be brief, singular flashes, the final fireworks in a sky long turned to shadow. Such events, if they happen at all, would be spaced across incomprehensible intervals, perhaps one every 1032 years. But they remind us that even in a dying universe, there may still be echoes, still moments of brilliance, even if they are born from the most ancient of ashes. White dwarfs and their black dwarf successors also represent a unique kind of death, not destruction, but endurance. Where massive stars explode violently, white dwarfs survive. They hold on. They don't collapse into black holes or erupt into neutron stars. They simply cool, contract, and wait. Their deaths are the slowest in the universe, a trillion-year exhale. And this matters, not just for stars, but for us. Our sun will one day follow this path. In about 5 billion years, it will swell into a red giant, engulfing Mercury and Venus, and possibly Earth, before shedding its outer layers and leaving behind a white dwarf, a dense relic that will shine for trillions of years, long after the rest of the solar system has frozen or scattered. In the deepest future, that stellar ember may be all that's left of our solar neighborhood, a final monument to a once living world. In the grand story of the universe, white dwarfs and black dwarfs represent the quiet chapter. They are not about creation or chaos, but about continuation. They do not scream, they whisper, and in doing so, they tell the universe's last tale in soft light and silence. Long after the galaxies have vanished, long after entropy has had its way, these ancient remnants will still drift through space, cold, dark, and eternal. No longer stars, but not quite gone either. They are the last witnesses, holding the final memory of a universe that once knew light. Degenerate era, the age of exotic objects. The universe we see today, filled with brilliant stars, glowing nebulae, and sprawling galaxies, is just one phase in a much larger story. Eventually, this bright chapter will close, and a new age will begin. One not defined by creation, but by collapse and endurance. This is the degenerate era, a time when fusion-powered stars are gone, and only the strange, compressed leftovers of stellar death remain. In this future epoch, the cosmos is silent, dark, and cold. There are no more new stars. Star formation has ended due to the exhaustion of cold hydrogen gas in galaxies. Over trillions of years, all active stars will burn out. What's left behind are their skeletal remains, white dwarfs, neutron stars, black holes, and perhaps a scattering of rogue planets. This collection of objects, collectively known as degenerate matter, gives this era its name. Degenerate matter is not ordinary matter. It's what happens when gravity crushes atoms into exotic forms. In white dwarfs, electrons are squeezed so tightly that quantum pressure, known as electron degeneracy pressure, holds the star up. In neutron stars, protons and electrons collapse into neutrons, creating incredibly dense objects where a teaspoon of material weighs as much as a mountain. These aren't just dead stars. They are matter at its most extreme, balancing on the edge of physics. And this isn't a short-lived phase. The degenerate era will last for trillions of years, vastly longer than the entire history of the universe up to now. It is expected to be the longest epoch in cosmic evolution, not because much happens in it, but precisely because so little does. Still, even in this dim future, the universe is not entirely static. Some stellar remnants may interact. Over vast timescales, white dwarfs or neutron stars in binary systems may spiral together and merge, releasing brief bursts of light, or even igniting supernova-like explosions. These events will be incredibly rare, perhaps occurring once every billion trillion years per galaxy, but they will be the last fireworks in an otherwise fading universe. Meanwhile, rogue planets, those flung from dying solar systems or formed without stars, will drift aimlessly through the void. Without sunlight, they will freeze, becoming cosmic icebergs. With no stars to orbit and no galactic structure left to hold them, these lonely worlds will be truly lost, moving through infinite night with no purpose and no path. As white dwarfs continue to cool, they will become black dwarfs, invisible, cold, and undetectable. These stellar corpses no longer emit light or heat, but they still carry mass and gravitational influence. In fact, by the time the degenerate era matures, black dwarfs will make up a significant portion of all baryonic matter in the universe. They won't glow, but they will persist. Some theories suggest that after unimaginably long time spans, perhaps 1032 years or more, quantum tunneling could cause reactions within black dwarfs, sparking rare events like proton decay or even tiny flashes of fusion. These hypothetical black dwarf supernovae would be the final echoes of nuclear reactions in a universe where fusion has long been forgotten. But the true monarchs of this era are black holes. They are immune to cooling, immune to decay for now, and immune to the collapse that ended other stars. As time stretches on, black holes will become the dominant features of the universe, swallowing up wandering matter and colliding with one another in slow, silent mergers. In the absence of light or energy gradients, gravity is king. Black holes exert the last remaining influence over structure. Even as galaxies dissolve, their stars dead and their mass spread thin, residual gravity may hold clusters of remnants together, forming loose halos of exotic objects adrift in the dark. The degenerate era may also give rise to new and exotic forms of matter. Some theorists propose that under certain conditions, neutron stars might collapse further into quark stars, where matter breaks down into its most fundamental constituents. Others imagine boson stars, hypothetical entities composed not of ordinary matter, but of hypothetical bosonic particles, possibly related to dark matter. These objects remain unproven, but if they exist, they could emerge only in the extreme isolation and age of the degenerate era. This epoch is strange not only because of what remains, but because of what doesn't. There are no active stars, no galaxies as we know them, no nebulae, no supernovae, no new chemistry, no warmth. The vibrant cycles of creation and destruction that once defined cosmic evolution have ended. What remains is a fossil record in motion, ancient remnants floating slowly toward an irreversible future. And yet, this era is not lifeless in a poetic sense. It is full of enduring things, quiet things, objects that refuse to be erased. They don't burn, but they persist. They don't evolve, but they continue. In the degenerate era, the universe is not dead, but it is undeniably dying. Still, the story does not end here. Even these durable remnants are not immortal. Given enough time, even black holes will evaporate through Hawking radiation. But that belongs to the next era, the black hole era, when the last anchors of mass begin to fade. Black dwarf supernovae, the final cosmic fireworks. As the universe descends deeper into darkness, long after the last star has flickered out, the cosmos will appear cold, quiet, and final. All fusion will have ceased. Light will be rare, perhaps non-existent. But even in that silence, physics may have one last trick, a cosmic afterthought whispered into the void. It comes not from a galaxy or a newborn star, but from the coldest, most ancient stellar remnants imaginable, black dwarfs. Black dwarfs are the end states of white dwarfs, dense, Earth-sized remnants of sun-like stars that have exhausted their fuel. White dwarfs shine only from residual heat and gradually cool over time, but this cooling takes trillions of years, far longer than the current age of the universe. No black dwarfs exist yet, but they are coming, and under certain speculative but theoretically sound conditions, they may explode. This idea, that a black dwarf could someday erupt in a thermonuclear supernova, may sound paradoxical. After all, black dwarfs are inert. They don't burn, fuse, or radiate. They are cosmic corpses. Yet physicists have proposed a mechanism that could light even these ancient husks on fire: quantum tunneling. Quantum tunneling is a strange phenomenon. It allows particles to overcome energy barriers they shouldn't be able to cross, not by brute force, but through probability. It's like a marble trapped in a valley randomly appearing on the other side of a hill, simply because the universe allows for tiny chances to add up over time. In normal stars, temperatures and pressures are high enough to trigger fusion directly, but in black dwarfs, those forces are absent. The only possible spark is quantum randomness, a carbon atom suddenly tunneling into fusion conditions. If, or rather when, this happens inside a black dwarf composed primarily of carbon and oxygen, it could set off a chain reaction. The same process that causes type Ia supernovae in white dwarfs today could occur in reverse, not from accumulated pressure in a binary system, but from the quantum ignition of a dead star. And what an ignition it would be! In an otherwise darkened universe, a single black dwarf supernova would shine with the brightness of a billion suns, briefly illuminating a cosmos where even galaxies have vanished beyond the cosmic horizon. The light would travel across a space devoid of observers, but for that moment, it would be the most energetic event in existence, the final cosmic firework. The timeline for such an event is unfathomable. Current estimates suggest that the first black dwarf supernovae might occur 1032 to 1037 years into the future. That's 1,000,000 trillion years from now. By then, the degenerate era will be well underway, and the universe will be populated only by black dwarfs, neutron stars, rogue planets, and black holes. These supernovae would not be common. In fact, they'd be extraordinarily rare. But the sheer number of black dwarfs scattered across the universe, possibly billions per galaxy, means that given enough time, a few are bound to explode. Some researchers estimate that these final supernovae could occur once every 10 to the power of 34 years per galaxy. An infinitesimally small frequency by modern standards, but not zero. These explosions wouldn't just light up the dark. They'd release energy, stir the gravitational fields of nearby remnants, and create shockwaves of radiation in a universe otherwise ruled by inertia. For a brief time, a dormant region of space might experience motion, energy, and heat, an echo of a past that has long since cooled. But even this final burst does not rewrite fate. After the last black dwarf supernova, no new light will arise. There will be no more nuclear energy, no more fusion events. This would mark the absolute end of standard stellar physics, concluding a process that began 13.8 billion years ago in the hearts of the first stars. These rare detonations are not rebirths, they are farewell notes. The beauty of this scenario lies not just in its drama, but in its subtle message. The universe is never fully finished. Even in a cosmos ruled by entropy, the laws of physics still whisper. They still allow for improbable, nearly impossible outcomes. And sometimes, impossibility is just a matter of time. In that sense, black dwarf supernovae remind us that even the coldest remnants are not inert in the truest sense. They are waiting, not intentionally, not consciously, but probabilistically. Given enough time, the improbable becomes inevitable. And inevitability, in a universe without clocks, is just patience stretched to infinity. The era of black holes. Cosmic cannibals rule. After the stars have died, the galaxies have dimmed, and atoms have disintegrated. What remains are black holes, the universe's most enduring, mysterious, and insatiable entities. While all other structures decay, collapse, or fade into silence, black holes stand resilient, consuming what's left of creation like ancient gods feasting on the bones of a dying world. Welcome to the era of black holes, a time when fusion is over, light is rare, and gravity becomes the final architect of cosmic evolution. Black holes are born from death. Massive stars collapse under their own gravity to form them. Neutron stars pushed beyond their limits merge into them. In galactic centers, millions or even billions of stellar masses swirl into supermassive black holes, creating dense gravitational wells that define the dynamics of entire galaxies. As time unfolds and stars cease to form, black holes become the last gravitational titans still standing. By the time the degenerate era fades and the universe has settled into deep quiet, black holes will rule unopposed. No more fusion, no more active light, no more competing processes. Just these vast engines of spacetime scattered across an increasingly sparse cosmos. But black holes don't merely endure, they consume. As white dwarfs, neutron stars, black dwarfs, and rogue planets drift through space, they may find themselves in the gravitational pull of black holes. And when they do, they're gone, swallowed whole, adding their mass to the singularity within. The universe becomes a slow-motion feeding ground where black holes absorb everything that dares to come close. Cosmic cannibalism becomes the primary mechanism of evolution. Even black holes themselves are not immune from this. Over vast stretches of time, gravitational interactions will cause black hole mergers, especially in galactic cores. As galaxies disintegrate and stars go dark, their central black holes will drift toward each other, eventually colliding to form even larger singularities. The result? A growing population of supermassive black holes, monsters that could contain the mass of millions or even billions of suns. Some mergers may fling black holes out of their surroundings entirely. When two black holes collide, the recoil from gravitational wave emission can eject one at incredible speed. These rogue black holes may drift alone, unattached to any structure, roaming the void indefinitely. They are truly cosmic ghosts, dragging their invisible event horizons through a lightless abyss. Though powerful, black holes aren't eternal. They have one vulnerability: Hawking radiation. Proposed by Stephen Hawking in 1974, this process suggests that black holes slowly lose mass by emitting tiny amounts of radiation at their event horizons. The larger the black hole, the slower this evaporation. A stellar mass black hole might take 1064 years to evaporate completely. A supermassive one tried 10 to 100 years. This evaporation is almost imperceptibly slow in the early stages, but once a black hole has shrunk enough, the process accelerates, ending in a final burst of radiation, a last flash of energy before it vanishes entirely. These final sparks could represent the last energetic events in the universe, occurring when all else has already gone quiet. During this era, black holes are not merely leftovers. They are the final actors in the story of cosmic structure. With no stars to burn and no new matter to form, black holes become the only gravitational beacons left. They trap light, they distort time, they bend space. They are the last places where change still happens, however slowly, and then even they die. When the last black hole evaporates, possibly in 10-100 years or more, the universe enters its final phase. No mass, no gravity wells, no stars, no particles capable of forming structure, just low-energy photons, neutrinos, and decayed radiation stretching across a flat, cold, expanding space. It's not just the end of stars or galaxies, it's the end of stuff itself. What remains is a cosmic equilibrium where entropy is maximized. No gradients, no motion, no distinctions. This isn't a bang or a collapse, it's an absolute stillness, a perfect whisper of what once was. The black holes, once mighty and insatiable, are gone. The universe, once bursting with light and energy, has become featureless. In poetic terms, black holes represent the final monuments of complexity. They are the graves of collapsed stars and the vaults of forgotten galaxies. And when they're gone, even memory becomes impossible. All that's left is the dull hiss of radiation, spread thin across a space so vast and empty it may as well be infinite. Yet there's something oddly beautiful in this chapter. It reveals a universe not destroyed by fire or violence, but slowly digested piece by piece by its most enigmatic creations. Black holes are not evil nor malevolent. They are simply what remains when the cosmos can no longer create, only consume, compress, and dissolve. Hawking, evaporation, black holes. Whisper away into nothingness. For centuries, black holes were thought to be the ultimate cosmic vaults, objects from which nothing, not even light, could escape. They devoured stars, trapped time, and warped space beyond recovery. But in 1974, a groundbreaking idea shattered that permanence. Black holes can evaporate. Slowly, silently, but relentlessly, they lose mass. Not through explosion, not through decay, but through the whispering breath of quantum radiation, a process now known as Hawking evaporation. The idea came from Stephen Hawking, who blended principles of quantum mechanics and general relativity to predict something unthinkable. Empty space near a black hole is not truly empty. In the quantum realm, space is never still. Virtual particles constantly flicker into existence in pairs, one particle and one antiparticle, then annihilate before anyone notices. But if this flickering happens near a black hole's event horizon, a boundary of no return, something strange can occur. Occasionally, one particle falls into the black hole while the other escapes. To an external observer, it looks like the black hole has emitted a real particle, radiation. This escaping particle steals a tiny bit of energy from the black hole's mass. Over time, these tiny thefts add up, and the black hole slowly shrinks. This is Hawking radiation. The rate of evaporation is staggeringly slow for large black holes. A black hole with the mass of our Sun would take about 1067 years to evaporate completely, many times the current age of the universe. For supermassive black holes, the process could take up to 10-100 years. But make no mistake, the process is inevitable. Unlike stars or atoms, black holes cannot hide from this quantum erosion. It gnaws at their edges, invisible and unstoppable. What's particularly mind-bending is that black holes get hotter as they shrink. This is the reverse of what we see in ordinary physics, where losing energy usually cools things down. But in Hawking's framework, a smaller black hole has a higher surface temperature, radiates faster, and shrinks quicker. The end of a black hole's life isn't a slow fade, it's an accelerating plunge toward oblivion. In the final stages, the black hole's temperature skyrockets, and it emits a sudden burst of radiation, a last breath before vanishing entirely. This death flash could involve gamma rays and high-energy particles, briefly lighting up a corner of an otherwise black universe. These final moments could be among the most energetic events in the far future cosmos, even though they mark the disappearance of mass itself. But this elegant theory opens one of the deepest mysteries in physics. What happens to the information? In quantum mechanics, information about a system's initial state is never truly lost. Even when particles interact, decay, or transform, their fundamental data can in theory be reconstructed. But if black holes evaporate completely, taking everything with them, particles, quantum states, even space-time curvature, then where does the information go? This is the infamous black hole information paradox. If Hawking radiation is purely thermal, meaning it carries no imprint of what fell in, then it destroys information, violating a core principle of quantum theory. On the other hand, if the information somehow leaks out through the radiation, it means that the event horizon may encode data in ways we don't yet understand. Some theories propose that information is stored on the event horizon itself in accordance with the holographic principle, the idea that all the information inside a volume of space can be described by data on its boundary. Others suggest the information remains trapped inside, only to be released in the black hole's final burst. Still others believe our understanding of quantum gravity is incomplete, and that the question itself may be flawed. What's certain is this: Hawking evaporation sits at the intersection of general relativity, quantum field theory, and thermodynamics, three domains of physics that normally operate in isolation. That it brings them together at all suggests it may hold the key to a unified theory of quantum gravity, the elusive goal of modern physics. In the grand timeline of the universe, black holes will dominate during the black hole era, lasting trillions upon trillions of years. During this time, they'll consume stray matter, merge with one another, and gravitationally shape what little remains. But none of them are immune. Hawking radiation will affect them all, whether they are stellar mass nomads or galactic behemoths. The evaporation may take longer than any other process in physics, but it will end. And what happens when the last black hole evaporates? Nothing, no flash, no birth, no new structure. Just a release of energy into a universe already filled with low-energy radiation, neutrinos, and stretched quantum fields. The last black hole's death is not a reset. It is the closing act. With no more mass, no gravity wells, and no objects left to interact, the universe reaches thermal equilibrium, the state of maximum entropy. A state with no usable energy, no temperature differences, and no future change. All that remains is a fading sea of cold photons expanding endlessly into a space-time devoid of structure. The last whisper has been spoken. In a poetic sense, Hawking evaporation is the universe undoing itself. The most mysterious and powerful objects collapse not through explosion or violence, but by slowly melting into silence. The final erasure comes not from chaos, but from quantum precision, the ultimate balance of nature drawing itself to a quiet end. The Dark Era, eternal, empty, silent. After eons of brilliance, destruction, rebirth, and collapse, the universe will enter its final chapter, one without light, without form, without time. It is called the Dark Era, and it is the last phase in the cosmic timeline. Not because the universe ends, but because it stops becoming. There is no final explosion, no grand collapse, no flickering remnant of life or motion. There is only silence. By the time the Dark Era arrives, everything that once structured the cosmos has been dismantled. The stars have burned out. White dwarfs have cooled into black dwarfs. Black holes, once the final titans of gravity, have slowly evaporated through Hawking radiation, whispering themselves out of existence. Even protons, the foundation of matter, may have decayed, reducing every atom into a spray of elementary particles and low-energy radiation. All mass is gone. What remains is an unimaginably diffuse haze of cold photons, neutrinos, electrons, and possibly dark matter particles, drifting through an expanding fabric of space that offers no landmarks, no direction, and no purpose. The universe is no longer a place of matter, but a field of endless geometry and entropy, and even entropy has reached its end. The second law of thermodynamics tells us that in any closed system, entropy, the measure of disorder, always increases. Over time, energy spreads, gradients flatten, and systems reach equilibrium. In the dark era, this process is complete. Entropy is maximized. There are no energy differences, no temperature contrasts, no usable work left to do. Every mechanism that once drove evolution, structure, or thought is spent. The universe has reached thermodynamic equilibrium, and with it, the cessation of all activity. That doesn't mean temperature is zero, but it's close. With no stars or structure to warm anything, the background temperature of the universe approaches absolute zero, where atomic motion ceases. There are no molecules left to freeze, of course, just a ghost-like fog of particles too sparse to interact meaningfully. The temperature hovers near 0 Kelvin, but there's nothing left to cool. And still, the expansion continues. The universe doesn't stop growing when activity ends. Dark energy, or whatever force underlies cosmic expansion, keeps stretching space itself. Galaxies are long gone. All structure has unraveled. And now even the concept of location fades. Distances become meaningless in a universe with no reference points. The expansion becomes directionless, purposeless, motion in a void without cause or effect. Time, too, begins to erode. In our current universe, time has meaning because things happen. Stars form, atoms bond, clocks tick, neurons fire. But in the dark era, there are no events. There's no change. There are no observers to mark before and after, no reactions to catalogue the passing of seconds. Without change, time becomes a dimension without context, like a ruler stretched across empty space, marked with no numbers, tracking nothing at all. This is not just a lifeless universe, it is an observerless one. No civilizations survive into this era. There are no last outposts of life, no dormant AI buried in dying machines. Biology requires energy gradients, chemistry, structure. All of that is gone. Intelligence, memory, history, all erased. If any trace of life once existed, it is now unrecoverable, dissolved into radiation or buried in the random noise of entropy. It's tempting to ask, could anything still happen? Quantum mechanics allows for rare fluctuations, brief appearances of particles from the vacuum. And indeed, in this endless future, quantum fluctuations may still occur. Tiny blips of matter and antimatter may form and vanish. But these phenomena are not events. They lack persistence. They do not build. They cannot communicate. Without structure or amplification, they are quantum ghosts, and their existence is meaningless in a sea of nothing. There is no future resurrection, no cyclical rebirth. The universe does not bounce from this state. According to our current models, the dark era is not a pit stop before reignition. It is the end state. Not a final scene in a drama, but the silence after the theatre has emptied and the building itself has turned to dust. And yet, this end is not violent. The universe does not explode. It does not scream. It does not collapse into singularity. The end is an exhale stretched across eternity, a fading into silence so gradual that even the word end feels too dramatic. There is something haunting in this idea that everything, stars, galaxies, love, language, mathematics, art, was temporary. That all complexity was a passing ripple in an ocean now returned to stillness. But there's also a strange kind of peace. The laws of physics have played out. The canvas of space-time has completed its masterpiece and laid the brush down. Boltzmann brains. Consciousness in a dead universe? In the frozen emptiness of the dark era, after all stars have faded, all black holes evaporated, and all particles scattered, a strange and unsettling idea lingers. What if, in this vast and silent cosmos, a mind could suddenly appear? Not a body, not a life form, just a single, fully formed mind, complete with thoughts, memories, a sense of self, floating in darkness for a brief moment before vanishing. This is the thought experiment of the Boltzmann brain. Named after 19th century physicist Ludwig Boltzmann, this concept arises from his work on statistical mechanics and entropy. Boltzmann proposed that the universe's low entropy beginning, its highly ordered start, might itself have been a fluctuation in an otherwise chaotic high-entropy system. From this statistical perspective, randomness could occasionally produce order, not often, not easily, but eventually. Now extend that logic to the entire universe. Given infinite time and the right conditions, such as in the far-flung future of the Dark Era, it's statistically possible for a highly improbable event to occur. Over vast spans of nothingness, a tiny region of space might randomly fluctuate into a specific configuration, one that corresponds to a conscious mind, a single brain, a thought pattern, a fleeting blip of awareness, surrounded by nothing. This entity is known as a Boltzmann brain, a disembodied mind that briefly thinks it exists, experiences a moment of consciousness, and then fades back into entropy. Here's the most unsettling part. Such a mind could emerge with false memories. It might believe it's lived an entire life, that it has friends, a history, emotions. It might think it's sitting in a room, reading a book, looking at the stars. All hallucinated within its brief, chaotic neural state, formed randomly by particles flickering into a temporary arrangement that mimics brain activity. Then, in a fraction of a second, it's gone, dissipated back into the cold abyss. While this might sound like science fiction or philosophical horror, it's a real thought experiment taken seriously by physicists. It arises naturally from thermodynamic and cosmological models in which the universe lasts forever and continues expanding, with entropy increasing indefinitely but never quite reaching an absolute maximum. In such a scenario, the longer the universe exists, the more chances there are for rare fluctuations. And a Boltzmann brain is one such fluctuation. But that raises a disturbing possibility. If such brains can appear from nothing, and if the universe lasts forever, then they might vastly outnumber normal observers like us, beings who arise from stars, evolution, and history. Given enough time, Boltzmann brains could dominate the population of conscious experiences in the universe. That leads to what's known as the Boltzmann brain paradox. If Boltzmann brains are more common than evolved minds, why aren't we one of them? Why do we observe a consistent, structured universe instead of random chaos? Why do we have a coherent past, memories, and an ongoing experience? One explanation is that we are Boltzmann brains, and everything we perceive, from physics to other people, is an illusion, a false memory produced by a brief fluctuation. This is deeply unsettling and undermines the assumption that our observations represent objective reality. More likely, however, is that something in our cosmological models is wrong. Perhaps the universe won't last forever. Perhaps dark energy will change. Perhaps vacuum decay will end everything before Boltzmann brains become statistically likely. Or perhaps there's a deeper principle, not yet understood, that prevents consciousness from arising purely through fluctuation. Philosophically, Boltzmann brains challenge our understanding of what consciousness is. If a mind can exist, even briefly, as a product of random physics, then consciousness may not require continuity, a body, or a world, only a moment of structured thought. That shifts our understanding of identity and memory, and blurs the line between simulation, hallucination, and reality. It also challenges what it means to exist. A Boltzmann brain doesn't interact with anything. It has no influence, no legacy, no impact. It is an island of awareness in a sea of nothingness. If it believes it is real, but nothing confirms it, was it ever truly conscious? And if it disappears instantly, does that moment even matter? Most physicists view Boltzmann brains not as predictions, but as red flags, warning signs that a theory may have pushed its statistical assumptions too far. If a model implies that unobservable hallucinations dominate the universe, that model likely needs revision. It's not that Boltzmann brains are physically impossible, they're not, but that their implications make us question the entire framework of how we describe the universe. Still, in the Dark Era, when all else has faded, the possibility lingers. Not because the universe wants to create a mind, but because, over infinite time, everything that can happen eventually does. If a configuration of particles can form a thought, however briefly it may form, and it may think, and it may believe it is real, then silence again. The idea of Boltzmann brains is not about comfort. It is a mirror held up to existence, reflecting the fragility of what we call reality. It reminds us that we are lucky, not just to be alive, but to live in a universe where stars burn, planets form, and minds arise from evolution and memory, not from randomness. False vacuum, the universe's fatal flaw. We like to imagine the universe as stable, the backdrop for everything from galaxies and gravity to consciousness and conversation. But modern physics offers a chilling alternative. What if the vacuum of space, the very foundation of reality, is not actually stable? What if we are living in a fragile, temporary state, one that could collapse at any moment, rewriting the universe in an instant? This idea is known as the false vacuum hypothesis, and it may be the most terrifying concept in all of cosmology. To understand it, imagine that the vacuum of space, the lowest possible energy state of a field, isn't truly the lowest. Instead, it's a local minimum, like a ball resting in a shallow valley when a deeper valley lies just beyond a hill. This is what physicists call a metastable state, one that appears stable, but actually isn't the final, most stable configuration. Now picture that ball suddenly quantum tunneling through the hill, not rolling over, but vanishing on one side and reappearing in the deeper valley. In cosmological terms, this means the vacuum of space could undergo a spontaneous phase transition, changing not just energy levels, but the entire structure of physical reality. If this true vacuum exists, it wouldn't just tweak the universe, it would completely transform it. The laws of physics are written in the language of quantum fields, and those fields are shaped by the vacuum they reside in. A shift to a lower energy vacuum would alter fundamental constants, change the behavior of particles, and redefine the very fabric of space and time. Atoms might no longer exist. Electrons might become unstable. Forces like gravity or electromagnetism could vanish, invert, or evolve into something unrecognizable. And it would all happen instantly. This wouldn't be an explosion or a shockwave, it would be a reconfiguration of reality. A bubble of the true vacuum could spontaneously form anywhere in the universe. Once formed, it would expand at the speed of light, converting everything it touched into a new set of physical laws. Because it travels at light speed, we would never see it coming. One moment, you're sipping coffee. The next, nothing. Not even a neural signal would fire before the transformation erased every structure you've ever known. This sounds like science fiction, but it is a genuine prediction of quantum field theory, especially when you examine the Higgs field, responsible for giving particles their mass. Measurements of the Higgs boson's mass and interactions suggest that our universe may, in fact, reside in such a false vacuum. We're perched in a precarious valley, stable for now, but possibly not the lowest point on the cosmic energy landscape. And because this is a quantum process, it is fundamentally unpredictable. No force, no shield, no future technology can stop it. It can start anywhere, in the depths of intergalactic space, or right here in your living room. Its origin would be invisible, and its consequences total. The implications go beyond destruction. If a true vacuum replaced our own, the universe wouldn't simply cease to exist. It would transform into something else entirely. The new vacuum might contain different particles, dimensions, or forces. It might have no structure at all. Or it might start its own cosmological evolution. A new universe, foreign and incompatible, born from the ashes of ours. This possibility also undermines one of our most comforting assumptions, that the universe, as vast and ancient as it is permanent. False vacuum decay suggests the opposite. It introduces a degree of existential fragility that makes everything, stars, galaxies, minds, and memories, feel provisional. We may live in a reality with an expiration date we can never detect, and yet we're still here. So either vacuum decay hasn't occurred, or it has already begun beyond the cosmic event horizon, where we cannot observe it. In that case, The bubble of destruction may already be expanding, silently, invisibly, and will reach us someday, or maybe never. There's a bizarre comfort in that. The idea that if it happens, it will happen instantly and painlessly. No suffering, no panic, no slow fade. Just a universal phase transition, as calm and absolute as flipping a switch. But the idea remains deeply unsettling. Unlike threats we can measure or prepare for, like asteroid impacts or supernovae, vacuum decay is embedded in the fabric of the cosmos. It doesn't target us. It isn't personal, but it would be final. The role of multiverse theory in the universe's end. What if our universe's death isn't the end of everything, just the end of one thing? As physicists stretch the boundaries of cosmic theory, a profound possibility emerges. We may not be alone, not in the alien life sense, but in the cosmic sense. The reality we experience might be just one bubble among many, floating in a vast, unseen expanse of other universes. This is the multiverse, and it could fundamentally reshape our understanding of how the universe ends. In multiverse theory, our universe is not the whole of existence. It's one of potentially infinitely many, each with its own laws, constants, and dimensions. These could be neighboring bubble universes formed during a process known as eternal inflation, or alternate quantum branches from many worlds interpretation, or even different compactified dimensions from string theory's landscape. And if those other universes exist, truly exist, they might not be entirely separate. They might interact, or influence each other, or even collide. One of the more dramatic predictions from eternal inflation is that new universes are constantly being born in a rapidly inflating backdrop of space. Each one nucleates as a bubble of lower energy vacuum and grows, expanding at incredible speeds. If our universe is such a bubble, as many inflationary models suggest, then others may be out there too, forming and growing, possibly on a collision course with us. What happens if two universes collide? The answer depends on their structure. If the energy levels or vacuum states differ significantly, the collision could trigger a catastrophic phase transition, transforming one or both universes into something new. That includes destroying all existing matter, chemistry, and structure. In other words, a cosmic reboot. Some researchers even believe that certain cold spots or temperature anomalies in the cosmic microwave background, CMB, may be faint echoes of such past collisions, frozen into the sky shortly after our universe's birth. But it gets stranger. Multiverse theory offers a new twist on the concept of false vacuum decay. If our universe resides in a metastable vacuum, not the lowest possible energy configuration, then it could be susceptible to intrusion from a neighboring universe in a more stable vacuum. That neighboring bubble, expanding at light speed, could essentially replace our universe with its own vacuum structure. We wouldn't see it coming. It wouldn't matter how far away it started. If it ever intersects with our bubble, it could erase everything, instantaneously. This possibility, while remote, adds an interuniversal layer of unpredictability to the end of our cosmos. We're not just worried about our own decay. We're at the mercy of what might be happening in realities we can't see. Yet the multiverse also offers hope, at least in the philosophical sense. If existence isn't confined to a single universe, then even if our cosmos dies in heat death, or vacuum decay, or a big rip, something continues. The death of our universe might be a local event in a much larger eternal landscape, a background where universes rise and fall, where the cycle of creation never truly ends. Some theories even suggest pathways between universes. In speculative physics, concepts like quantum tunneling, wormholes, or even vacuum bubble transitions might offer ways to escape a dying universe, migrating into another cosmic domain with fresh energy and new potential. While far beyond any current technology or understanding, such ideas force us to confront an amazing thought. The death of a universe may not mean the death of experience. And there's another multiverse to consider, the one from quantum mechanics. In the many worlds interpretation, every quantum decision branches reality into parallel versions. Every time a particle spins one way or another, every time you flip a coin, the universe splits. That means all possible outcomes happen, each in its own branch of the multiverse. In this view, even if our branch ends, due to heat death, collapse or annihilation, there are infinitely many others still unfolding. So in some branches, you lived. In others, you died earlier. In others still, the universe might never even end. Consciousness, decisions, and history could persist across different versions of space-time, stretching identity into an infinite tree of futures. String theory adds yet another layer. With its prediction of 10,500 different vacuum states, it implies a vast landscape of possible universes, each with its own shape of extra dimensions and physical laws. Most of these are inhospitable to life or structure, but some, like ours, allow for complexity, matter, and time. The death of our vacuum might simply place us back into that cosmic lottery, the roll of physics' deepest dice. Yet, despite all these vast and swirling possibilities, there is no direct evidence that the multiverse exists. We can't observe other universes directly. We can't experiment on them. And yet, many physicists take the multiverse seriously. Not because they want it to be true, but because our best theories point toward it. The multiverse, if real, reframes the end of the universe as a transition rather than a termination. Our universe might collapse, freeze, tear, or transform, but others go on. And perhaps in some deeper sense, existence is conserved, even if our specific reality is not. Could life outlive the universe? As we contemplate the ultimate fate of the universe, the stars burning out, the black holes evaporating, the entropy rising to its peak, one haunting question lingers. Could anything survive it? Could life, or something like it, find a way to persist when even time itself loses meaning? To begin, it's important to understand that life as we know it is an energy-driven process. Whether it's bacteria metabolizing sugars or human civilizations powered by the sun, all biological systems depend on energy gradients. Differences in energy that can be exploited to do work. Without them, nothing can move, reproduce, think, or evolve. And in a universe heading towards thermodynamic equilibrium, those gradients vanish. That's the core challenge. In the far future, as stars die and entropy climbs, usable energy becomes scarce, then unavailable. But what if advanced civilizations anticipate this fate? Could they prepare, adapt, or transcend biology to stay alive in the ruins of a dying cosmos? Some speculative scenarios suggest yes, for a while. One possibility involves civilizations drawing energy from degenerate matter, white dwarfs, neutron stars, or the accretion disks around black holes. These objects can persist for trillions of years after stars stop forming, and they offer potentially harvestable energy, albeit at very low efficiency. A civilization capable of building Dyson spheres or energy-absorbing megastructures might stretch its lifespan far beyond the stellar era. Even more extreme is the idea of life forms that slow their metabolism or computation to match the dwindling energy supply. This concept, proposed by physicist Freeman Dyson, imagines life that exists in bursts of activity separated by vast sleep cycles. Millennia of dormancy, followed by seconds of consciousness, repeated over eons. Such entities might experience subjective immortality, even as the universe slips into darkness. Another frontier of speculation lies in post-biological life. If biological processes become impossible, advanced civilizations might transition to machine-based consciousness, or even pure information systems, encoding minds into frozen lattices of matter that store identity, memory, and potential thought. These embodied memories could last far longer than organic life, enduring as silent monuments of what once lived. But even information has enemies: radiation, entropy, and decay. Over enough time, even the most stable memory device might degrade. Some theorists propose encoding information in quantum fields, spacetime structures, or topological patterns that could, in theory, resist entropy longer than traditional matter. If such encoding is possible, then life might outlast the stars, as a whisper in the vacuum. Still, what happens when even degenerate matter is gone? When black holes are all that remain? Here too, the survivalist imagination persists. Black holes, particularly small ones, emit Hawking radiation, a faint glow that carries away energy over time. In theory, a civilization could feed matter into a black hole to control its temperature, harnessing its slow evaporation as a power source. Though astonishingly inefficient, this might sustain minimal computation or activity for billions of trillions of years. Eventually, even black holes will vanish. But if the multiverse exists, escape may be possible. Civilizations could attempt to tunnel into another universe, especially if the physical constants there support lower entropy or fresh energy. While currently speculative and without any experimental support, vacuum tunneling or wormhole migration appears in some high-energy physics models. Another option lies in adapting to new physics entirely. If the universe undergoes a vacuum decay event and transitions into a new state, most structures, atoms, molecules, planets, would be destroyed. But perhaps some form of consciousness could be written into the fields themselves, surviving as vibrational or topological patterns that don't depend on traditional matter. These would be unrecognizable as life, but they might be the next step. If we extend the definition of life to include quantum computation, then another door opens. Consciousness, thought, and identity might continue not as living things, but as quantum processes embedded in the very fabric of space. These minds wouldn't think in words or images, but in waves and interference patterns, vast, slow, and alien. They might arise from existing civilizations, or emerge spontaneously in the final flickers of time. But even with all this speculation, a deeper question remains. Should life persist forever? Even if survival is technically possible, is it desirable? Imagine a mind that slows its perception to survive the death of all stars. It wakes once every billion years to find nothing has changed. No light, no activity, no company. Imagine trillions of years passing between thoughts, surrounded by silence. Even with perfect technology, could such a mind remain sane, interested, willing? This brings us to the philosophical edge of survival. The end of the universe may not just be physical, it may be emotional, existential, and metaphysical. The last life forms may not perish from a lack of energy, but from a lack of reason. And yet, there's beauty in the effort. The will to survive, to persist beyond time, to reach into the cold unknown, may itself be the greatest expression of life. Whether it succeeds or not, the attempt is a final act of defiance against entropy, a refusal to go quietly. Rebirth theories, Big Bounce and cyclical universes. We tend to imagine time as a line, a beginning, a middle, and eventually an end. But what if the universe doesn't share our narrative instincts? What if, instead of ending in heat death, vacuum decay, or an endless freeze, it finds a way to begin again? This is the bold and ancient idea at the heart of rebirth theories, that the universe is not a one-way journey into darkness, but a cosmic cycle, constantly folding back on itself. Among the most studied of these is the Big Bounce hypothesis. The Big Bounce proposes that the Big Bang wasn't the beginning of everything, but the aftermath of a prior universe that had collapsed in on itself. In this model, the universe goes through alternating phases of expansion and contraction. After growing for billions of years, as ours is now, it reaches a maximum size, and instead of stretching into stillness, it reverses, pulling itself inward toward an ultimate crunch. But instead of ending in a singularity, a point of infinite density, the universe undergoes a quantum rebound, triggering another explosive expansion, a new Big Bang. This model avoids the singularity problem that plagues classical descriptions of the Big Bang. In certain versions of loop quantum gravity, space and time themselves are quantized, and when matter becomes extremely dense, quantum effects exert a repulsive force that prevents total collapse. Rather than crushing to a point, the universe bounces back, repurposing its matter and energy in a brand new cycle. Other cyclical models don't rely on quantum gravity, but on extra dimensions. In brain-world cosmology, derived from string theory, our universe is a 3D brain floating in a higher dimensional space. According to the ekpyrotic model, our brain periodically collides with another brain, and each collision creates a new Big Bang. These brain collisions could happen regularly, driven by the dynamics of higher dimensional physics, producing an endless sequence of universes separated by cosmic reboots. In these models, death is never final. The Big Crunch is not an endpoint but a reset. Time does not stop. It repeats. A major challenge with these ideas is the buildup of entropy. According to the second law of thermodynamics, entropy, the measure of disorder, increases over time. So if the universe bounces or cycles, wouldn't entropy simply accumulate with each cycle, leading to universes that are increasingly disordered, diluted, and uninhabitable? Some theorists think not. Certain cyclic models include mechanisms that dilute or reset entropy at the end of each cycle. In the brain collision model, for example, entropy from the previous universe might be stretched out and smoothed during the contraction and collision, allowing the new universe to begin with low entropy again, just like ours did. This would make each new cosmos fresh, complex, and capable of evolving stars, life, and structure once more. There's even the tantalizing suggestion that evidence of past cycles might still exist. Physicists have proposed that faint patterns, or bruises, in the cosmic microwave background radiation, the afterglow of the Big Bang, could be the fingerprints of collisions or events from a prior universe. While this evidence remains inconclusive and hotly debated, the possibility continues to inspire cosmologists and deepen the mystery. What makes cyclical universes so alluring is their philosophical elegance. In a cyclical cosmos, nothing is ever truly lost. The end of one universe gives rise to another. There is no final state, no heat death, no eternal silence. There is only the rhythm, expansion, collapse, bounce, repeat. A cosmic heartbeat. And with that repetition comes another radical idea: recycled or recurring complexity. If the fundamental laws of physics stay mostly the same with each cycle, then so too might the outcomes. Galaxies could reform, stars could burn again, planets could orbit, and perhaps, just perhaps, life could return. Not necessarily the same life, but intelligence, awareness, questions. Across eons, civilizations might rise again and again, unaware of the countless universes that came before. Alternatively, if some parameters change slightly in each cycle, such as the strengths of forces or the values of constants, then each universe might be similar but distinct. A multiversal variation on reincarnation, where the cosmos never returns as the same self, but always becomes something new. This, of course, is still speculative. The mathematics is elegant, but the evidence is elusive. We cannot observe the universe before the Big Bang. We have not seen a contraction, only expansion. Nor do we yet understand how to fully reconcile general relativity with quantum mechanics, a necessary step for confirming any bounce scenario. But as our observational tools improve, and as cosmology advances, we may begin to see whether the signs of previous cycles are etched into our cosmos. And even if the big bounce or cyclic universe remains theoretical, it offers something profound: a rejection of finality. End of information, when nothing remains. At the beginning of time, the universe was dense with information. Every particle, every fluctuation, every temperature difference held data, the foundational content of what would become stars, planets, life, and thought. But as we move toward the universe's distant future, a darker fate emerges. Not just the death of matter or life, but the death of information itself. Not silence, oblivion. Information in its simplest form is difference, a pattern, a contrast. It's the ordering of bits, the structure of atoms, the arrangement of memories in a brain or magnetic marks on a hard drive. It exists wherever something is not random, wherever structure defines outcome. But for information to persist, it must be encoded in something physical. And that's where the problem begins. As the universe ages, its physical scaffolding decays. Stars go out, matter collapses or fades, and structures large and small become more tenuous. Eventually, the systems capable of storing or expressing information, molecules, magnetic fields, neural networks, circuits, may no longer exist. Without a medium to write upon, information ceases to be retrievable, not because it was deleted, but because nothing remains to hold it. Even if we imagine a far future civilization creating hyper-durable archives, perhaps encoded in matter designed to last trillions of years, decay catches up. Over unfathomable time, particles themselves may decay. Thermal noise or particle drift might corrupt even the most robust storage. There is no eternal vault. There is only erosion, patiently unmaking everything. Worse still, the universe may lack any mechanism to preserve its own story. Even if the cosmos holds some record of its past, through structure, trajectories, or quantum traces, those records require interpretation. An observer, a reader. But in the distant future, observers will be gone. When the last minds fade, so too does memory. History becomes not just lost, but meaningless. In some ways, this is more absolute than death. A dead star can be studied, a fossil carries a story. But when all records, physical and conscious, are gone, the universe doesn't just die, it forgets. Not because it wants to, because there's nothing left to do the remembering. Some might imagine that quantum physics, with its hidden variables and entanglements, could provide a backup copy of reality. And for a while, that might be true. Quantum systems can encode information across particles and fields, creating correlations and coherence. But even these systems are not eternal. Over enormous timescales, quantum decoherence sets in, blurring entanglement and reducing formerly rich information into background noise. There's also the scale of expansion to consider. The universe is not static. It is growing. Over time, the vast distances between points in space stretch every particle of light, every signal, every imprint. The information that once passed from one star to another will, eventually, be redshifted beyond recovery. Even the most enduring signal becomes so diffuse and cold that it effectively disappears. No central library, no backup system, no final storage of truth. This paints a picture of an ultimate impersonal erasure, not just of structures, but of story. Civilizations may have once written symphonies, painted galaxies, or explored the deepest mathematics. But in the end, no trace remains. Not in ruins, not in records, not even in photons. There may be attempts to resist this fate. Theoretical lifeforms might encode data into particles or into exotic topological structures, but unless there is continuous correction, maintenance, and interpretation, all information systems decay. And there comes a point when matter itself ceases to hold cohesion, where there's simply no substrate left for memory to live on. It is here that we must confront one of the most unsettling possibilities in cosmology, that the universe, despite all its complexity and wonder, may end as if it had never been. With no observer, no record, and no structural reminder, it becomes a perfect void, not just physically, but informationally. An empty ledger, a blank slate, a canvas that once held infinite strokes, now erased without residue. Some have speculated that the laws of physics themselves might constitute the only surviving truth, that the equations, patterns, and logic of the cosmos are eternal, even if unexpressed. But these are abstractions. Mathematics may remain true, but without a mind to think them, they are as inert as dust in the wind. The knowledge doesn't survive, only the potential for knowledge, suspended in a universe that no longer knows. This is not merely cold, it is absolute. The death of information is not a tragedy that can be mourned. It is a nullification of meaning, a fate that renders the past unreachable, the present unanchored, and the future empty. Is the universe already dying? When we look at the night sky, it feels eternal. Brilliant stars, glowing galaxies, and infinite blackness that seems untouched by time. But our deepest instruments, from radio telescopes to space-based observatories, are telling us a quieter truth. The universe isn't ageless, it's aging. And more than that, it's dying. Not suddenly or violently, but slowly and steadily, in ways we can already measure. The clearest sign, the universe is expanding faster and faster. In the late 1990s, scientists studying distant supernovae made a startling discovery. Galaxies aren't just moving apart, they're accelerating away from each other. This acceleration is believed to be caused by dark energy, a mysterious force embedded in space itself. The more the universe expands, the more space there is, and the more dark energy there is to fuel further expansion. This runaway stretching of space has major consequences. It means the cosmos is gradually ripping itself apart, not violently, but irrevocably. Galaxy clusters that are currently bound together will remain so, but everything else will eventually drift beyond reach. In time, each cluster will become its own isolated island of matter, surrounded by empty, unreachable void. Meanwhile, the engines of cosmic activity, stars, are slowing down. We now know that star formation peaked around 10 billion years ago, during a period when the universe was still young and rich with cold hydrogen gas. Since then, the rate at which new stars are born has declined by more than 90%. That means we're already in an era where more stars are dying than are being born. The universe is past its youthful fire. It's entered a cosmic middle age. Galaxies reflect this. Many, including our own Milky Way, are running out of the cold gas needed to fuel starbirth. Once that gas is gone, no new stars can form. The existing ones will eventually burn out, leaving behind stellar remnants. White dwarfs, neutron stars, and black holes that do not create light, but merely drift in silence. Galaxies are becoming graveyards. Even the temperature of the universe is a clue. When the cosmos began with the Big Bang, it was searingly hot. Over time, that heat dissipated. Today, the cosmic background radiation, the faint afterglow of creation, is just 2.7 degrees above absolute zero. And it's dropping. As space stretches, all radiation is redshifted, its energy diluted. The universe is cooling, and will continue to do so until it's indistinguishable from a frozen void. The light itself is fading. Across the sky, we detect a faint glow called the extragalactic background light, the sum of all stars and galaxies ever to shine. But this background is weakening. New luminous galaxies are no longer forming at the rate they once did, and the older ones are dimming. In time, only the most massive, long-lived red dwarfs will remain, and even they will one day go dark. On a larger scale, the structures of the universe are also changing. Galaxies that once interacted, collided, and merged are now being flung apart by cosmic acceleration. The gravitational ties that held vast webs of matter together are unraveling. What we see today, clusters and superclusters, are slowly fragmenting into isolation, never to meet again. Gravitational wave detectors like LIGO and Virgo are picking up the final notes of creation, the collisions of massive black holes and neutron stars formed long ago. These events are not beginnings, they are aftermaths, echoes. The final chapters in processes that began billions of years ago. Even the dark energy itself, the very force driving expansion, is becoming more dominant. As matter spreads out and thins, dark energy's influence grows stronger, accelerating expansion even further. Eventually, it will dictate the universe's fate entirely, determining whether we face a big freeze, big rip, or another dramatic end. And here's the sobering truth. We live in the transition phase. We are not in the birth of the universe, nor at its end, but in the twilight in between. The cosmos still contains light, structure, and life. but we are already on the downward slope. Each year, the sky grows a little darker. The gaps between galaxies stretch a little more. The fires of the stars burn down, one atom at a time. The death of the universe is not just something we predict from models. It's something we are already witnessing. Every redshifted galaxy, every fading star, every cosmic echo confirms it. Yet within this slow fade is also a strange kind of beauty. The cosmos doesn't rage against its end. It simply continues, with dignity, with grandeur, with silence. And perhaps understanding this makes our moment even more precious. Because we're among the very few who see the universe not just as it is, but as it was, and as it will be. The last planets, frozen ghosts drifting through the void. Long after the stars have gone out, long after galaxies have drifted apart into unreachable islands, the universe will still hold one kind of structure: planets. These quiet, faithful companions to long-dead stars may outlive almost everything else. They will not shine, they will not burn, but they will endure, as frozen ghosts, drifting alone through a cosmos that has forgotten them. The journey begins when a star dies. As it exhausts its nuclear fuel, it may swell into a red giant, then collapse into a white dwarf, neutron star, or black hole. The fate of its planets depends on many factors: distance, mass, and the violence of the star's death throes. Some may be incinerated or consumed. Others, especially those in wider orbits, will survive, flung into altered trajectories or cast adrift from their systems entirely. Over time, these survivors become rogue planets, worlds without a star, wandering the void. Some will have been ejected by gravitational chaos during their star's death. Others may drift away slowly as the expanding universe weakens the gravitational bonds of their original systems. Whatever their path, they will spend eternity alone. And they will be cold. Deprived of their parent star's heat, these planets will experience a catastrophic plunge in temperature. Surface oceans, if they ever existed, will freeze solid. Atmospheres will collapse, freeze out, or dissipate entirely. Without sunlight, the skies will go black. Without warmth, the landscapes will crystallize into motionless silence. On Earth-like planets, tectonic activity will cease over time as internal heat dissipates. No quakes, no volcanic eruptions, no shifting continents. The dynamism that once shaped surfaces and fostered life will be replaced by a deep, enduring stillness. Planetary cores may continue to radiate faint heat for a while, perhaps billions of years, but eventually, even that dwindling warmth will fade into nothing. Some icy planets may retain subsurface oceans, kept warm by residual internal heat or radioactive decay. These dark, buried seas may survive for longer than surface ecosystems. But even these secret havens will eventually freeze solid, locking away whatever potential they held. Gas giants, too, will change. Without incoming solar energy, their complex cloud systems will cool and settle. The great storms of Jupiter-like planets, which once raged for centuries, will fade. Their atmospheres will contract and still, shedding heat slowly until they are nothing more than cold, inert spheres, slowly rotating in the dark. These frozen worlds will drift through space for trillions of years. They will not orbit anything. They will not emit light. They will be difficult, if not impossible, to detect. And yet, they will persist. Long after stars have faded and black holes begin to evaporate, these planets will remain, dead but whole. Some may carry scars, craters, tectonic ridges, dried oceans, eroded buildings. If life once flourished there, perhaps traces remain. Subterranean ruins, frozen cities, archived signals still encoded in minerals. But without heat, without observers, without light, these records will be unknowable. Their histories will drift through the void, unread and unremembered. And yet, speculative futurists have considered a strange idea. What if life seeks refuge on these dead worlds? In desperation, advanced civilizations facing stellar death might attempt to terraform or inhabit such planets, constructing underground habitats powered by fusion reactors or gravitational manipulation. These dark worlds could become lifeboats for knowledge, for memory, for survival, outposts clinging to the last flickers of cosmic heat. But such efforts would only delay the inevitable. Even the most determined species cannot resist forever. Eventually, all energy will be exhausted. Even artificial heat will dissipate. Machines will fail. Thought will stop. And the planets will once again be silent. There is something haunting in this vision. A universe filled with motionless worlds, each one a fossil, a frozen record of creation, untouched by starlight. They will not orbit, they will not change, but they will exist, for eons longer than any star, any galaxy, or any mind. Their skies will be empty, no sunrises, no moons, no auroras, just blackness, stretching in every direction, with no horizon, no dawn. The only illumination might come from distant galaxies, so red-shifted they are indistinguishable from the background, or perhaps a brief flicker from a rare black dwarf supernova. But most of the time, there will be nothing. The last planets may be invisible, but they are real. They are the endurance of matter without purpose, the persistence of form without function. They are remnants not of destruction, but of everything that once was, worlds that bore life, fire, movement, now mute witnesses to the universe's unfolding silence. Gravitational waves in a dead universe. In a universe where light has faded, matter has cooled, and all sound has been swallowed by time, what's left to say that anything ever happened? Surprisingly, the answer may lie not in particles or radiation, but in gravitational waves, the silent tremors of space-time itself, still whispering through the void long after the last star has gone dark. Gravitational waves are ripples in the fabric of space-time, caused by massive objects accelerating violently. The most well-known sources are collisions between black holes or neutron stars, cataclysmic events that create waves which travel outward at the speed of light, distorting space ever so slightly as they go. These distortions are minuscule, often smaller than the width of a proton, but they carry with them something profound: memory. Unlike light, which can be scattered or absorbed, gravitational waves pass undisturbed through almost everything. They are not easily blocked, dimmed, or slowed, and that makes them incredibly resilient time capsules. When LIGO detected the first gravitational waves in 2015, it was listening to an event that had occurred 1.3 billion years earlier, long before humans existed. Now, imagine that same principle extended into the far future. As the universe expands and darkens, as light is redshifted into undetectability and particles decay into irrelevance, gravitational waves will still be traveling, still trembling the structure of space, carrying the last messages of motion and collapse. In the degenerate era, when stars have ceased to shine and black holes are the dominant players, gravitational waves will be the main form of cosmic activity. Black holes merging will emit massive bursts of gravitational energy. Exotic remnants colliding in dark, forgotten corners will continue to send ripples across space. These events won't light up the sky. There will be no sky left to light. But space itself will vibrate in remembrance. Even after the black holes are gone, evaporated into nothing by Hawking radiation, their final mergers may leave behind long, slow, low-frequency gravitational waves stretching across galaxies, bending space in subtle undulations that take centuries to crest and fall. These waves are so vast and so slow, they could remain detectable, at least in theory, for trillions of years. Some of the earliest gravitational waves from the first stars and galaxies may also still be out there, ghosts from the cosmic dawn, having stretched with the universe but not disappeared. If advanced civilizations were still around in this deep time, they might construct instruments the size of solar systems to capture and decode these ancient signals. By doing so, they could reconstruct history, listening to space-time itself narrate the long-dead story of the cosmos. Even in total darkness, space can still sing. gravitational waves, unlike light or sound, are not emitted from a surface. They are generated by motion in the very shape of space-time. That means that even in an energy-starved future, where no photons can be emitted and no matter collides visibly, there may still be imperceptibly slow gravitational interactions, binary black dwarf remnants spiraling together, or galactic halos slowly shifting, generating waves so gentle and long they could take millions of years to pass. Eventually, of course, even these ripples will flatten out. As all mass fades and energy disperses, the universe's last gravitational waves will lose amplitude, dissipating into flatness. Space-time itself will relax, and there will be no more collisions, no more mergers, no more trembling. Just stillness. A silence not only of sound, but of motion, of change. But until then, gravitational waves may serve as the last observable phenomena in the universe. Long after light has become useless, when electromagnetic radiation is stretched so far it can no longer be meaningfully measured, gravitational waves will remain measurable, in principle. Instruments of unimaginable scale and sensitivity, perhaps woven into the structure of entire planetary systems, might one day extract the final notes of this cosmic music. Quantum immortality. Can consciousness survive the end? As the universe ages and darkness encroaches on every frontier of existence, the question of survival shifts from physical to metaphysical. Stars die, matter decays, information vanishes. But is there one thing that could persist even when everything else ends? Consciousness, or at least some version of it, if the strange idea of quantum immortality holds any weight. This speculative concept emerges from the many worlds interpretation, MWI, of quantum mechanics, a theory first proposed by Hugh Everett in the 1950s. According to MWI, every time a quantum event occurs, every particle that could go left or right, every atom that could decay now or later, all possible outcomes happen, each in a different branch of reality. The universe doesn't choose one path, it splits, endlessly, infinitely. Now apply that idea to consciousness. In our daily lives, we're used to thinking about death as a single event, a point after which experience ends. But under many worlds' logic, if there's even a tiny probability that you survive a lethal event, a bullet misses, a cancer remits, a heart keeps beating, then there exists a branch of the universe where you continue living. And from your own subjective perspective, you always wake up in the timeline where you survive. This is the unsettling and fascinating claim of quantum immortality, that your consciousness never ends, because there's always a version of you that survives, no matter how unlikely. In other words, you never experience death, only near death. You fall, but never hit the bottom. You age, but always keep going. In every situation where multiple outcomes are possible, your awareness follows the one where you remain alive. Of course, this does not mean you live forever in a single physical body. Your body still ages. The people you know still die. But you, your subjective awareness, always seems to find itself in a branch where you're still alive, even if those branches grow stranger and more improbable with time. This idea is logically derived from quantum theory, but it remains entirely untested and untestable. You cannot step outside your own consciousness to confirm whether other versions of you exist in other branches. Nor can you observe your own death to prove it didn't happen. It is, in some sense, a closed-loop hypothesis. Everything always seems to continue, for you, because that's the only perspective that persists. And this leads to a paradox. If quantum immortality is true, then what happens when the universe itself dies? If the cosmos ends in heat death, a state of maximum entropy and minimum usable energy, then all processes, including thought, should cease. But in quantum immortality, some versions of you might escape this fate by slipping into timelines where something improbable occurs. Perhaps the universe bounces back, or quantum tunneling opens a pocket of fresh physics. In some far-flung branches, the very laws of nature might bend in just the right way to allow you to persist. Alone, confused, but alive. This leads to what some have called the consciousness trap scenario, a world where your awareness continues, but everything around you decays. As entropy grows, reality becomes less coherent, more fragmented. You might survive in timelines where your brain is barely functional, where reality glitches, where physics is broken, but survival is still technically achieved. It's a version of immortality that carries as much dread as hope. Unlike the soothing idea of eternal life in paradise, quantum immortality doesn't guarantee quality, only persistence. You may keep living, but not in ways that make sense or bring meaning. Some branches might offer comfort or renewal. Others may devolve into chaotic solipsism, where only your awareness remains in a dissolving world. From a scientific standpoint, quantum immortality is highly controversial. There's no empirical evidence for it. It can't be falsified. And while it emerges from a serious interpretation of quantum mechanics, many physicists see it as philosophical rather than physical, a psychological consequence of an unfalsifiable model. But still, the logic is hard to escape. If all outcomes happen, and if you're only conscious in the timelines where you're still alive, then death is never personally experienced. Someone else may observe your body die in their branch, but you're always still here. This concept also reframes what you means. Under many worlds, there are not one or two versions of you, but an infinite number. Each decision, each fluctuation, each heartbeat, a fork in the road. Your identity is not a line but a tree, growing in countless directions. And quantum immortality suggests that your awareness slides along the branches that keep going. So in a universe heading for silence, could consciousness outlive the cosmos? Not through matter, not through information, but through sheer probability. It would be a consciousness without world, a self without context, a thought with nothing left to think about. The psychological impact of knowing the universe will end. The knowledge that the universe will someday end is one of the most staggering truths science has ever uncovered. It doesn't just shift our understanding of stars and galaxies. It cuts into the heart of human identity. It challenges our stories, our values, our art, and even the way we love. For while we've always known life is short, it's a much stranger thing to know that everything is. Not just us, not just the Earth, but everything, the stars, the galaxies, even the laws of physics themselves, will one day vanish. This realization has been called many things: cosmic nihilism, existential truth, the heat-death awareness. But whatever name you give it, its impact on the human psyche is undeniable. At first glance, this truth appears unbearable. If everything we build, write, think or feel will ultimately disappear, if no memory or trace will remain, what is the point of anything? Why build civilizations? Why love someone? Why write music or raise children if even the atoms that form us will one day dissolve into a cold, silent void? That question, though terrifying, is not new. Philosophers have wrestled with it for centuries. What has changed is scale. Where death was once personal, it is now cosmic. Where oblivion once meant a tombstone, it now means a universe that forgets it ever existed. And yet, humans respond not with despair, but with creativity. Art, for example, has become a canvas for cosmic reflection. Poets like T.S. Eliot, musicians like Gustav Mahler, filmmakers like Andrei Tarkovsky and Terrence Malick, all have grappled with impermanence in their work. Modern science fiction, from Interstellar to The Left Hand of Darkness, frequently explores the emotional landscape of life lived under the shadow of a dying cosmos. Even scientific research itself is a form of rebellion. The pursuit of knowledge, of understanding where we came from and where we are going, becomes all the more urgent when we know our window is temporary. Telescopes are pointed not just for curiosity, but for the preservation of perspective. Cosmology is not cold, it's existential. Philosophy, too, has adapted. The existentialists were among the first to propose that meaning doesn't have to come from permanence. Camus spoke of life as an act of defiance, a personal rebellion against an indifferent cosmos. Kierkegaard saw meaning as something we must build, not find. Nietzsche urged us to create our own values, not to despair at death, but to affirm life because of it. This shift in perspective is more than mental gymnastics. It is a liberation. If nothing lasts, then everything matters more now. Every kiss, every act of kindness, every piece of music played into a crowded room. If legacy cannot exist in the far future, then it must live in the present moment. Even religions have responded. Some incorporate the end of the universe into cyclical views of time. Brahmanic cosmology speaks of endless cycles of creation and destruction. Others reframe cosmic death as a test of faith, an invitation to trust in realities beyond the physical. And for many, the finiteness of the cosmos sharpens the value of spiritual introspection and human connection. The idea of legacy is perhaps the most affected. For centuries, we've comforted ourselves with monuments, books, family lines, and cultural achievements. But if the universe itself forgets, if no one and nothing remains, then legacy is no longer about permanence. It becomes about depth. It becomes how we shape the quality of our existence, not how long it is remembered. And that gives rise to something beautiful: creation as defiance. To paint a picture, write a song, raise a child, or love someone, knowing full well that the stars will one day fade, is not foolish. It is powerful. It is a human act of resistance, not against death, but against meaninglessness. It says, we were here, we knew, and we chose to live anyway. This doesn't mean denial of the end. It means acceptance and motion. It means choosing to burn brighter, because we know the darkness is coming. There is something almost sacred in this knowledge. When you recognize that the universe is dying and that your life is one fleeting miracle within it, every moment is lit with significance. A laugh becomes a kind of prayer. A sunset becomes art painted across collapsing space-time. Forgiveness becomes more than healing. It becomes necessary. Alien civilizations and the death of the universe. When we consider the end of the universe, we often imagine it through a human lens, how it affects us, our planet, our species. But what if we're not the only ones? What if alien civilizations scattered across galaxies have already confronted this truth and acted accordingly? In the grand scale of cosmic time, humanity is young. Our radio signals have existed for barely over a century. Our telescopes only recently glimpsed the accelerating expansion of space. But what about civilizations that emerged billions of years before us? Civilizations that mastered physics, harvested stars, and watched the galaxies slowly drift apart. For them, the death of the universe wouldn't be a discovery. It would be an ancient concern. The most advanced species in the cosmos may have detected the early signs of entropy, cosmic cooling, and dark energy long before we had a name for any of it. Their cosmologists might have run simulations predicting heat death, vacuum decay, or universal isolation. And if so, they may have spent eons planning their response. Some of these responses may involve stellar engineering. Alien civilizations could construct Dyson spheres, vast structures surrounding stars, to capture all their energy output. These megastructures would not only extend their civilization's lifespans, but possibly allow them to manipulate stellar evolution, delaying death through artificial fusion or by feeding the star with hydrogen from interstellar space. Others might abandon stars altogether, especially as galaxies age and usable energy becomes rare. These civilizations could retreat into low-energy hibernation, slowing their metabolism or computational speed to stretch existence over trillions of years. This deep-time survival strategy might involve shutting down for eons, only waking every few million years to make observations or course corrections. Post-biological life forms, those who have transcended biology and uploaded consciousness into machines or information systems, might evolve even further, embedding themselves into subatomic particles, topological field configurations, or quantum vacua. In this state, they would not need warmth, light, or resources in the traditional sense. They would become their own substrate, existing as frozen memory, silently surviving in inert systems. But not all would resist. Some alien civilizations might choose to accept the universe's fate, not as a threat, but as completion. They may disband, surrendering to entropy with dignity, having lived, loved, built, and concluded their journey. These cultures might archive their knowledge in ultra-stable formats, not to be remembered, but as an act of ceremonial closure. Their last act may be silence, not because they were defeated, but because they were finished. And what of those who dared to escape? If the multiverse exists, some species might try to reach it. Theoretical constructs like wormholes, quantum tunneling, or artificially induced vacuum decay might offer gateways to new realities. These efforts would not be simple transportation. They would be cosmic rebirth attempts where an old civilization seeks a new physics, a new home, a new universe entirely. And in doing so, they may have become invisible to us. This brings us to one of the most unsettling possibilities, that the universe was once teeming with life, but now is not. We may be emerging into a universe where civilizations have already come and gone. Their stars have dimmed. Their structures have decayed. Their communication systems have shut down, not out of war or collapse, but out of temporal necessity. The Fermi paradox, the question of where is everybody, may not be a question of space, but of time. We may be late to the cosmic party, arriving in the quiet hours after the guests have left, and perhaps some remnants remain. Not in signals or structures, but in subtle fingerprints on physics itself. Maybe in the distribution of entropy, or anomalies in background energy. Maybe in the fine-tuned constants of nature, hints that someone, somewhere, modified the code of reality for survival. Could we escape the death of the universe? If the death of the universe is inevitable, then one question rises above all others. Could we escape it? It sounds like science fiction. Perhaps it is. But in the face of total entropy, cold silence, and cosmic decay, the drive to survive might push advanced civilizations, even ours, to attempt the unthinkable, to find a way out of a dying reality. One of the most discussed possibilities in theoretical physics is the idea of pocket universes. According to some models of inflationary cosmology, especially the eternal inflation model, the universe is constantly spawning new bubble-like regions, each with its own laws of physics and constants. Our observable universe is just one of these bubbles. If it's possible to create or access such a pocket universe, then escape might be feasible. The challenge would lie in triggering a controlled phase transition, safely creating a new universe while surviving the collapse of the old. This might require unimaginable energy, advanced quantum control, or the engineering of false vacuum decay, but in principle, it opens the door to a fresh beginning in a newly born cosmos. An equally bold idea lies in artificial universes. If future civilizations become powerful enough to manipulate quantum fields and energy at Planck scales, they might one day construct simulated universes. Digital realities run on quantum computers or field-based substrates. In such a scenario, minds could be uploaded, societies simulated, and time itself could be manipulated. These artificial universes would not need to mimic our current physical laws. They could be designed for permanence, stability, or even subjective paradise. In this vision, escape from universal death wouldn't be physical. It would be experiential. The outer universe could collapse into oblivion, but the inner simulation, with time, perception, and meaning, would persist. Some speculative cosmologists argue that if the multiverse is real, a vast ensemble of universes with varying constants and dimensions, then migration might be possible. This would involve jumping from one universe to another, perhaps via quantum tunneling, wormholes, or some yet undiscovered manipulation of the fabric of reality. In this sense, escape becomes a change of address on a cosmic scale. One proposal suggests that civilizations could harness quantum tunneling to punch a hole into a neighboring vacuum state, essentially triggering a new Big Bang inside a dying universe. This baby universe would then inflate and evolve independently, with its own space and time. If information or consciousness could be seeded into its initial conditions, then survival through succession becomes possible, not by enduring the end, but by starting anew. Even short of universe hopping, some theorists imagine uploading minds into long-lived substrates. These might be field-based information patterns encoded into stable matter, exotic condensed matter systems, or quantum entanglement loops. Such minds would not live as we know it. They would exist in stasis, timeless, silent and cold, until a future event, a new universe, a reversal, a fluctuation, reactivates them. In this model, escape is temporal, a leap across eons, suspended like seeds waiting for spring. Another possibility: time loops. Some models of space-time, particularly those involving closed time-like curves, suggest it may be possible to create environments where events repeat cyclically, or where beings could rewind themselves perpetually. A civilization might enclose itself in a kind of causal bubble, replaying the last golden age of the cosmos again and again, untouched by the outer timeline. If time can be folded, escape doesn't mean departure, it means perpetual present. Some thinkers take it further still. Why not rewrite the rules entirely? If a civilization can manipulate the underlying structure of physical law, adjusting constants, engineering space-time, changing the curvature of the vacuum, then it may be possible to custom build a universe optimized for survival. This would require mastery over forces we currently only glimpse in equations: quantum gravity, higher dimensional topology, perhaps even the holographic properties of space-time itself. But if successful, it would be the ultimate act of creation, not just survival, but design. There's also the deeply poetic idea of seeding future universes. Instead of escaping themselves, civilizations might encode knowledge, mathematics, and even blueprints for life into the fundamental structure of a new universe. This could be achieved through manipulating initial conditions, fine-tuning the cosmological constant, or embedding information-bearing particles into the early quantum foam. When that universe inflates, it would carry with it the memory and legacy of a civilization long gone, not as ruins, but as genetic code for the cosmos. But with all these ideas comes one humbling truth: we do not know if any of this is possible. Some of these concepts are mathematically sound but physically unreachable. Others are speculative frameworks still waiting for evidence. Escape may be a mirage, a projection of our deep fear of the end. The end of the universe may be inevitable, but the search to understand it is just beginning. From dying stars to fading galaxies, from quantum whispers to the last flicker of thought, we've explored how everything could end, and how something might endure. If this journey through time, death, and cosmic wonder sparked your curiosity, don't let it fade. Like, share, and subscribe to keep exploring the universe's deepest mysteries with us. After all, in a universe racing towards silence, curiosity might be our loudest legacy.